Hello everyone, this is Lecture 5 of ComSci 174, Convolutional Neural Networks. In this video, we will discuss convolutional neural networks, or CNN. But first, we have to discuss perceptrons, which are the basic building blocks of neural networks. And then, we will discuss neural networks in general before proceeding with convolutional neural networks. We will look at convolution filters and other CNN layers. And finally, we'll also look at some architectures for the CNN. Okay, so let's start. In the previous video, we were introduced to the classification problem. So you're given data as the input, we pass it to the classifier, and we will output a class label from a fixed set of categories. However, usually, our data is not passed as is to the classifier. So we don't pass in raw data to the classifier. We first convert it into something called a feature vector. Okay, so what is a feature vector? So let's take this one for example. Let's say you're doing a spam classifier or a spam filter. So of course your data would be email messages, right? Now you will not pass the whole email message to the classifier, but instead you will extract some features of the email, and then that is what you'll pass to the classifier. Okay, so maybe some spam features that you determined were the presence of the word buy, the presence of the word cheap, number of spelling errors, number of exclamation points, non-alphabet in words, and all capital words. So those are all indicators of a spam email, right? And so for each email that you'll pass into the classifier, you will compute these features. So maybe for email 1, there are 3 presence of the buy word, 1 time nag-appear ang cheap, 5 times it has spelling errors, 7 times an exclamation point, and so on. Okay, and then for email 2, you do the same. So it looks like email 2 is not spam because it rarely has some spam features, whereas email 1 has a lot of spam features. So more likely this is spam, right? So instead of passing in the whole email message, we will just pass in this feature vector with just a bunch of numbers. So 3, 1, 5, 7, 18, 10. That is what we will pass for email 1, and then for email 2, we'll pass in 1, 0, 1, 0, 2, 0. Okay? So that is feature vectors. So usually we do some kind of feature engineering. So from the raw data, we will try to pick out the features that are relevant. So for example, here we have ID, first name, last name, year of birth, age, gender, and then the choice, right? So the choice would be the output label, so whether they picked A or B. We have 6 features, but really we only need 2 of them because we don't need the ID. It doesn't matter what their first name or last name is. The year of birth could be a factor, but that's also related to the age, so we'll just pick age instead. Okay, and then the gender could be a factor as well. So instead of passing all of these 6 features here, we will just pass in age and gender. Okay, so you have the ages here, and then for the gender, we encoded it F as 0, M as 1, and then for the choice of A or B, A becomes 0, B becomes 1. So it becomes a feature vector, and the labels are also becomes numerical. Okay, so that is what we do when we feature engineer. So we try to pick out the best features to use for our classifier. Okay, but sometimes we might want to use everything as well. Okay, so let's say for example, for an image, let's say it's a 28 by 28 image, and you want to use all the pixel information, so you can just stretch this out from a 28 by 28 matrix into a 1 by 784 vector. So you're just flattening out the matrix. Okay, so you're using all of the pixel values. That's possible as well. Okay, now in most classification problems, we have multidimensional features. So we usually have 3 or more features that we use. So it becomes multidimensional, right? So in this example, there are 3 features, so we can plot it in 3D. Now if it's 4 or more features, then it becomes harder to visualize. But in here, since it's in 3D, we can plot it in 3D, and then there's a plane that separates the two classes, right? And then in most cases also, it is a multi-class classification problem, not a binary classification problem. So if it's binary classification, you only have two classes. If it's multi-class, then it's three or more. Okay, so in this one, there's a 4-class problem, right, in this example. But before we dive into multidimensional features and multi-class classification, let's start first with a simple problem, which is the binary classification, which means that there are only two classes. So in this example, you have the blue and the red class, and there are only two dimensions or two features. So you have so we can plot it in 2D, okay? And the other thing is, it's also linearly separable. So we can draw a line to separate the two classes, okay? So we'll start with this very basic problem, and then we'll expand into the multi-class classification and non-linearly separable data later on. Okay? So let's start with the perceptron. The perceptron is a simple linear binary classifier. So binary classifier meaning it can only classify two classes, and linear meaning it can only separate linearly separable data like this one. Okay? So it's a linear binary classifier, and it's the basic building block of neural networks. So in the perceptron, we will try to learn the weights and the bias associated with input data to give the correct output. So the perceptron will look something like this. So if these are your inputs, x1, x2 up to xm, then you will have weights in the perceptron that are associated with each input. So you have weight 1, weight 2 up to weight m. And then you also have a bias term, okay? And then you combine this input with the weights, combine them through a weighted sum, and then pass it to an activation function to produce an output. Now don't worry if the terms weighted sum, activation function don't seem familiar yet. We will discuss what they mean in a while. But basically, everything inside the red box is part of the perceptron, okay? So the weights and the bias, you do the weighted sum, and then the activation function to produce the output, okay? Now, perceptrons are inspired by neurons, or the nerve cells in the human body. So for the input, you have the dendrite. The nucleus acts as the activation function, and it decides whether to fire the signal, okay? And then the axon will process the output, okay? So perceptrons are inspired by neurons. So for the perceptron, it receives features as the input, and then for the output, of course, the class label, which is either 0 or 1, because again, this is only a binary classifier. And then the weights for the perceptron will try to determine how important is this feature for the classification, okay? So is feature 1 important? Is feature 2 less important? Is feature 3 very important? And so on, okay? And the weights are what we learn during training, okay? So you can think of the weights as when you're training and trying to figure out the weights, you can think of it as like you're kind of like a sound engineer who's tuning and tweaking and turning all these knobs and sliding these levers to make the best sound possible, and in turn make the best perceptron model possible, okay? So you're tweaking a lot of weights or a lot of parameters so that you can find the best possible model, okay? So that's the analogy for weights. Now the perceptron model is a line, because as we said, it separates linearly separable data. So the line is just a decision boundary that will separate the data, and remember that the line has the form y is equal to mx plus b, or the slope-intercept form, right? Where m is the slope and b is the bias, right? So if the line's formula is y is equal to mx plus b, the perceptron has a similar formula, which is y is equal to wx plus b, where w is the set of weights, x is the input, and b is the bias term. And then y, of course, is the output that you produce. Okay. So you'll notice that it has a very similar form to the line, and because of that, if m is the slope, w, which is the weight, also controls the slope of the line. So it controls whether the line is steep, or is it kind of flat, or the angle of the slope, basically. And the bias will allow you to shift the line up or down. Okay, so for example, here we have 4 different perceptrons. So for example, the black, the green, the red, and the blue perceptron. So for this one, it has kind of a steep angle. This one is the red one is kind of okay angle. The green one is just horizontal, right? And then the black one is just vertical. Okay, so it's a line that separates the data. Okay, so the black one is bad because there's a lot of blue dots that are on the other side of the line when it's supposed to be on the left side, right? And then the green one is kind of okay because everything is above, everything above it is blue, everything below it is red, although these 2 points here are already near the boundary, so that might not be safe. So I think the best one here, the best perceptron, is the red one, because there's a lot of margin of error. Yeah. So yeah, but that's basically a perceptron. The model is a line that separates the data, and the weights will control the slope. Okay, and the bias will let you move the line up or down. Okay. Now, we talk about the weights and the bias separately, but really we could combine them into one vector. So the weight vector could be represented as follows. So you have the weights w1 up to wn, and then you put the bias term in front. And then for the input vector, you have your usual input x1 up to xn, and then you put a 1 in front so that it will become paired with the bias term. Okay, so that later on when we multiply them, bias will be multiplied with 1, the weight 1 will be multiplied with x1, and so on. Okay, so the weight vector is an ordered list. Don't shuffle it because they are supposed to correspond to the specific input items, right? So for example, input x1 should be multiplied with weight 1, input x2 should be multiplied with weight 2, and so on. Okay, so they should be aligned. Okay, you don't shuffle them. So how does the perceptron work? Okay, so how do we use it? So we basically compute the weighted sum of inputs using the associated weights. Okay, so we do this by performing a dot product of the input vector and the weight vector. So both the input vector and the weight vector are vectors of numbers anyway, right? So we'll just do a dot product, and the result of that will be passed to an activation function that will decide if the output is 0 or 1. Okay, so the output is 1 if the weighted sum is greater than 0, otherwise the output is 0. So let's say, for example, we have this perceptron. So the input is 1, 2, 3, and 4, and then the weights are all 0.25. So we'll do 1 times 0.25, 2 times 0.25, 3 times 0.25, 4 times 0.25, and then we'll add all of that up. And since this sum is greater than 1, then we will output the positive category here. Okay, so that activation function is called the step activation function. So if it's if the input is greater than 0, then it will output 1, else it will output 0 in here. So that's the step activation function. Okay, so how does a perceptron learn? We mentioned the perceptron having weights, but how does it get these weights? Okay, so let's look at the process of perceptron learning by using error as a feedback. Okay, so we will start with a random line for the perceptron, and then we will set the number of repetitions, also known as epochs. This is usually a large number, let's say 1000 or 10,000. And then we'll also set the learning rate, which is a small number that we'll use to update the line or the weights. Let's say 0.01. Okay, and then we'll repeat the following. Okay, we'll pick a random data point, and if it's already correctly classified by the line, then we won't do anything because anyway the line correctly classifies it anyway. But if it's misclassified, then we will adjust the line using the learning rate towards the data point that was misclassified. Okay, so let's see an example of that. Let's say this is our data set. So let's start with a random line. Okay, maybe a random line looks like this. Okay, and for our line, everything above it should be red and everything below should be blue. Okay, so we'll already notice that for this random line we have a couple of items that are misclassified, right? So for example, this 3 here are misclassified because blue should be below, and then this 3 here are also misclassified because red should be above. Okay, so let's try to pick a random point, and let's say we pick this one. Now this is misclassified, right? So what we'll do is we'll adjust the line towards this data point. Okay, so maybe now our line will become something like this. So instead of having that like this earlier, we'll move it towards this point here. So maybe something like this. Okay, so let's say that the line is something like that. Okay, so now we have correctly classified the random data point, okay, this one, but there are still misclassified items, right? So let's try to pick another random data point, and maybe it's this one. And then this data point is also misclassified because blue should be below the line, right? So what we'll do is we'll adjust this line towards the misclassified data point. So from here, maybe we can make the line, so instead of something like this, we can adjust the line towards it to make it something like that maybe. Okay, so now this data point is already below the line, but again this is still not perfectly correct, right? So let's pick another random data point, and maybe it's this one right here, and it's also misclassified because it's above the line, so it should be below because it's blue. So we'll move the line again towards it, so maybe the line will now become something like this. Okay, maybe something like that. And then after a few more iterations, we can find that this is already a correct model because it now clearly separates the blue dots from the red dots. Okay, so that is an example of how the perceptron learning works. Okay, start with a random line and then pick a random data point. If it's misclassified, then you move the line towards it to correct the line basically, and then if it's already correctly classified, then don't do anything. Okay, so yeah, that's how you learn, that's how your perceptrons learn the weights. Okay, now that only works for linear data. Now what if your data is non-linear? So what if you need like a circle to separate the blue ones from the green ones, right? So our current perceptron no longer cannot handle it, right? So for the perceptron, the single layer only works for linear data, but if we stack them together later on to a multi-layer perceptron, then that forms a neural network, and it will now work for non-linear data. Okay, So we started with perceptrons because they are the building blocks of neural networks, but our end goal is to, well, to learn about neural networks, and those are the ones that can process non-linear data. But even the perceptron itself is only limited to linear data because if we do weighted sum, that's basically just a linear combination, right? So your computing power is only limited to linear functions, right? So if you want to have the power of non-linearity, then you need to add non-linear activation functions. Okay, so what are activation functions, first of all? So the activation function, we already saw one earlier, the step activation function. Its input is the weighted sum, right? Remember that the perceptron takes the weighted sum of the inputs and combines it with the weights, right? And it will perform some math operation on the input, and it will decide whether the neuron should be activated or not. So either 1 or 0, right? So what are some of these activation functions that also provide non-linearity? So first example is the sigmoid function, having this equation here, 1 over 1 plus e raised to negative x. So it kind of squashes the weighted sum to the range 0 to 1. Okay, but the problem is it's not zero-centered. So the sigmoid here is not zero-centered, right? Because everything is above 0. Okay, whereas hyperbolic tangent kind of looks similar. It has a similar looking curve, but this one squashes the values to the range -1 to 1. So this one is zero-centered, and because of that, hyperbolic tangent is actually preferred over sigmoid. So very rarely do you see sigmoid being used because hyperbolic tangent is preferred over it. Okay. Next, we have a simple activation function called ReLU, or the rectified linear unit, and it's pretty simple. If it's less than 0, then it will output 0, but if it's greater than 0, then it will output the same number. So y is equal to x if it's greater than 0, but if if x is less than 0, then y is 0 as well. Okay, so you're basically thresholding it at 0. Okay, so everything dies at 0, and then the line continues greater than 0. The problem with ReLU is that you have the dying ReLU problem, wherein if most of the activations here are 0, then you kind of stop learning because none of the neurons are being activated, right? So to fix this, there was an improvement called the leaky ReLU function. So instead of outputting 0 if it's less than 0, then you multiply it with some alpha, okay, some factor to make it smaller, but not exactly 0. Okay, so it fixes the dying ReLU problem because it doesn't output exactly 0 if x is less than 0. Okay, so there's a whole lot of other activation functions out there, so you can just choose however whatever you want, but usually the ones that are prevalent in practice are hyperbolic tangent and ReLU. Okay, so that is the perceptron. Okay, the basic building block of your neural network. So again, it takes in weights. It learns the weights of the inputs, okay, and combines it with the bias, and then you take the weighted sum, and then the weighted sum is passed to the activation function, which is now usually non-linear, okay, to improve the computing power of your perceptron, and then the activation function will decide whether the output is 0 or 1. Okay, so that is the perceptron. Okay, so now we are ready to discuss neural networks. So what are neural networks? They are a biologically inspired classifier that uses interconnected group of nodes. Okay, so it's inspired by a network of neurons in the brain, and it's used in machine learning, computer vision, natural language processing, and other AI fields. So neural networks look like this. Okay, so you have a bunch of nodes or perceptrons that are connected to each other. And you have three types of layers, which are the input layer, the hidden layer, and the output layer. Okay? So the input layer, of course, accepts the input data. The output layer will output the answer that we're looking for. And then the hidden layers are all the layers in between the input and the output layers. Okay? Now, what is the purpose of the hidden layers? The hidden layers will try to learn the weighted connections of different data features. So they will try to combine the different features. So what if I try to combine feature 1 and feature 2? Is that a good indicator of what the class will be? Or how about if it's feature 1 and feature 3, or feature 2 and feature 5, and so on? So it will try to learn different combinations of features. Okay, and the strength of those connections will be the weights, okay, that we'll try to learn. Now, the neural networks have multiple layers because we want to, instead of having like one giant complex model, okay, that tries to do everything, we will try to break it down into smaller successive models. So each layer will try to do its own thing, okay, and then it will pass off what it learned to the next layer, and then the next layer will try to do something that's a little bit more complex. Okay, so the layers as we go deeper have an increasing complexity. Okay, so that is why we have multiple layers in neural networks, because we try to break down a complex model into smaller successive models. Okay, now if we talk about the network's architecture, then we are talking about the number of layers that it has. So there could be like 3 hidden layers, or 4 or 5, and so on. Okay, so the number of layers and the connection structure. So there could be fully connected structures or skip structures, and so on. Okay, so that will refer to the network's architecture. Okay, so the layers of the neural networks are connected. So if the output of the previous layer can be considered as the next layer's input. Okay, so we feed the output of the previous layer in as the input of the next layer. And since they're connected, the node connections in successive layers have associated weights, as we mentioned, and these weights are learned during training. Each layer also has a separate activation function that applies non-linearity. So you could have like a ReLU activation in layer 1 and then maybe sigmoid in layer 2. But in practice, we usually use the same type of activation function throughout the whole network, okay, to keep it uniform. Okay. Now, our perceptron was a linear binary classifier, right? But for our neural network, it can classify non-linear data because now it has multiple neurons that allows it to have more computing power. So it's not just linearly separable data, it can also process non-linear data now. And it's also not just limited to binary classification, it can also perform multi-class classification. Okay, so neural networks are more powerful than perceptrons. So let's take a look at some neural network types. Okay, the first one is the multi-layer perceptron, or MLP. For multi-layer perceptrons, this is a feed-forward network, which means that data only goes forward. Okay, and the layers are made up of perceptron nodes. And the thing about MLPs is that they are fully connected. Okay, that this means that each node in one layer has connection to each node in the next layer. So full connections. So all nodes in layer 1 is connected to all nodes in layer 2. Okay, and these are usually used for classification and speech recognition tasks. So this is an example of a multi-layer perceptron, or an MLP. Okay, so yeah, you'll notice all of the neurons here are connected to all of the neurons on the next layer. Then all of the nodes here are also connected to the nodes on the next layer, and so on. So that is multi-layer perceptron. Next, of course, we have the convolutional neural networks, which we'll discuss in detail in the later part of the video. It uses convolution and pooling layers, and it's usually used in image and pattern recognition. So we'll just pass by it quickly because we'll dive into it deeper later in the video anyway. Okay, so this is an example of a convolutional neural network. Okay, so it has convolution layers, non-linear activations, pooling, and then it also has a fully connected layer at the end for the classification. Next, we have generative adversarial networks, or GANs. Okay, and what they do is they try to create new data instances that resemble the training data. Okay, so they are used in creating realistic images, photos of human faces, and in rendering 3D objects. So this is the generative part. Okay, it creates new data that's similar to the training data. Okay, so examples of this are photorealistic faces. So these faces here that you can see are generated by a GAN. Okay, of course you're familiar with deepfake. Okay, you have a target actor, and then you apply yourself, and then you kind of create like a fake video of the target actor that seems to look like you. Okay, so be careful about these types of videos. And then you can also have like fun stuff like automatic anime character creation. So just by looking at tons of anime characters, the GAN can also create its own anime character images. Okay, and then you have photos to emojis, so automatic creation of emojis just by from photos of humans. Okay, and then face aging, so you try to estimate how a face would look like if it's aged by, let's say, plus 10 years or plus 20 years and so on. Okay, or even going backwards from here, it's from 30 years old, what would it be if it was 10 years old? Okay, and you'll notice it's quite similar to the ground truth. Okay, like this, so you can also do that. And then there's also super resolution, which is you're given a low resolution image and you try to create a higher resolution image, like let's say 1080p or 4K resolution that looks exactly the same, but you started with a low res image, let's say 144p, and then create a much bigger resolution. Yeah, so you're kind of upscaling the image. Okay, so that's also another application of a GAN. Now, how does it do this? Okay, so a GAN kind of looks like this. It has two parts: the generator model and the discriminator model. Okay, so the generator is what creates the new data, and the discriminator kind of differentiates between the real data and the generated data, and they have opposing goals. So the goal of the discriminator is to separate the real from the fake, okay, or the generated data. But the goal of the generator is to fool the discriminator or the critic. So that is the adversarial part of the generative adversarial network. It's because the generator and discriminator are kind of fighting. Okay, the generator wants to fool the discriminator, and the discriminator wants to catch the generator's lies, basically. So it's kind of sharpen iron sharpens iron, right? So if the two of them try to one up the other, then they become better at both of their jobs. Okay, so that's generative adversarial networks, which are kind of popular nowadays too. Okay, next we have something called the recurrent neural networks, or RNNs. So this is when your neuron output is fed back as input to itself. Okay, so that's why it's recurrent, because you loop the output back as an input. Okay, so this is used in chatbots or text-to-speech apps. So it kind of looks like this. Okay, so the output here of H is fed back as input back to H, basically. So if you try to unravel that or unfold it, the H at time -1 is being fed to HT, and then this is not yet at time ht, this is not yet known, but you'll know it after you do ht, and then it will be fed back to the the node itself. So yeah, that's recurrent neural networks. And then you also have the long short-term memory network, or LSTM. Okay, it's a type of RNN that learns and memorizes long-term dependencies. So it's useful in time series predictions and in speech recognition and in music. So it kind of looks like this. Okay, so it's still RNN, but it's more tuned to long-term dependencies. Okay. Next, we also have the autoencoder. Okay, so it's a feed-forward network wherein the input is the same as the output. So what does this mean? So what we do for the encoding part is that we try to compress the input into a lower dimensional code and try to reconstruct the output from the code. Okay, so it's kind of a dimensionality reduction network. We try to compress the input and try to reconstruct it with the code that we produced. Okay, and see if that code is sufficient enough to produce the output that kind of looks similar to our input. Okay, so this is how the autoencoder looks like. So the encoder will try to encode this data into some code. Okay, and then given that code, it will pass it to the decoder part, which will try to now recreate the given data, but with fewer dimensions. Okay, so it's a dimensionality reduction. So it's used for compression. Okay, so those are some of the useful neural networks. Of course, there are other types like self-organizing maps. You have your deep belief networks, restricted Boltzmann machines, and others. Okay, so if you're interested in those other network types, you can also look them up if you want to. Okay, but for this video, we'll focus on convolutional neural networks. Okay, so the model of the neural network consists of the connection weights and the node bias. So the model will kind of look like this. So you'll notice that the connections from one node to another have associated weights, right? And each node here also has an associated bias on top of it, right? So those numbers are the bias terms. So that is what your neural network model will try to learn. So the weights and the biases. Okay. Now, we said that the neural network is more powerful than the perceptron. So earlier we showed that the perceptron can only deal with linearly separable data, but for our neural network, it can deal with non-linear data, right? So maybe our data has a complicated boundary, which kind of looks like this. So because we have a lot of neurons or perceptrons, you can think of it as each neuron is like trying to figure out a boundary. Okay, and with a combination of those linear boundaries, we can actually recreate the non-linear boundary that governs our data, basically. So you have a lot this multiple perceptrons here. All of them will try to draw a line, and then the intersection of everything would be this one right here. Okay, so that is why we have multiple layers, multiple perceptrons. Okay, now now that we have the network model, okay, assuming that we have a neural network model, how do we use it? Okay, so we call this step the forward propagation or the forward pass, and we do this using matrix multiplications. So we do matrix multiplications from the input layer to the different hidden layers all the way up to the output. Okay, so as we mentioned earlier, since they are connected, the previous layer's output matrix will become the next layer's input matrix. Okay, so we feed it forward. So what happens in each layer? So in each layer, you have the input matrix. Okay, at the start, this would be the input data itself, right? And then the weight matrix, so the weights for that layer, and we do a dot product. okay, or sorry, not the dot product, but the matrix multiplication, and it will produce the output matrix. Okay, so after that, we also have to process the bias. Okay, so for the output matrix, we need to add the bias matrix of that layer. Okay, so since remember, each layer has a weight and a bias. Okay, so we'll do matrix addition, and then after that, we will apply the activation function. Okay, so that could be ReLU or hyperbolic tangent or step or sigmoid and so on. Okay, and then the output matrix here will be fed as the input matrix of the next layer naman. Okay, so yeah, the cycle the flow continues, or we keep feeding it forward until it reaches the output layer. So let's see an example here. Okay, let's see. So our input here is a matrix of size 3 by 1, right? This is 3 by 1, and then for the weights here in this layer, there are two weights, so from x to h1 and x to h2. So we put that here in this weight matrix. That is a 1 by 2 matrix. So if we multiply a 3 by 1 with a 1 by 2, we produce a 3 by 2, right? That is what we have here. So this is the intermediate result, right? Then after that, we will add the bias. So we'll add the bias to this one, add the bias to this one, and add the bias to this one. Okay, and then after adding the bias for h1 and h2, we'll apply the activation function. Let's say it's ReLU, so we'll apply it here, and then after that, this will now become the input for the next layer. And for the next layer, we have 4 weights, right? So h1 to o1, h1 to o2, then h2 to o1, h2 to o2. So we have a 2 by 2 matrix here. So this one was 3 by 2, right? And then this is a 2 by 2 weight matrix. So if we multiply this 2, we will produce a 3 by 2 output matrix because of this one, 3 by 2, right? So we have a 3 by 2 output, and then of course we'll add the bias again. So we'll do that. We'll add that for each row here, and then it will produce the final output, and then we'll apply the ReLU. Okay, so that is what we do for forward propagation. Basically just a bunch of matrix multiplications and adding the bias. Okay. However, there is something called the bias trick, wherein we don't have to separately add the bias, but instead incorporate it to the weight matrix so that we only do one matrix multiply. Okay, so how does this happen? So basically, if we're doing the matrix multiplication, right? So this one is 3 by 4, right? 3 by 4, and then this one is a 4 by 1. So the output should be 3 by 1, right? So let's say that we have a 3 by 1 output here. Okay, so what will we put in here? So maybe we'll add blue. So this one will be multiplied with this matrix here. So 0.2 will be multiplied with 56, negative 0.5 will multiplied with 231, 1 to 24, 2.0 to 2, and then we will add all of those up, and that will be the value here for our first one. And then for the next one, for the next line, we will do the same thing but for this row. So 1.5 to 56, 1.3 times 231, 2.1 times 24, and then 0 times 2, which is 0. And then if we add all of those up, that would be the second entry. And then for the third one, let's say we have this one, so this row here, 0.25 to 231, 0.224, then this one, and then add all of them up, then this one, the third. And then these three values will add this with the bias, and then it will produce another 3 by 1 output. Okay, so it's still another 3 by 1 output, but we can do away with doing this. Okay, doing a separate matrix multiplication and then an addition. We can just incorporate the bias as an extra column for the weights, and then for the input we will add an extra 1 here. And the reason why is because we're doing this anyway, right? So we're doing this multiplied with this, which was this one, which is the first one. Not that one. Which was supposed to be this one, the first one, right? And then we add it to 1.1. So since we're just adding it anyway, then we just have add 1.1 here multiplied by 1 directly. Okay, and then for the next row, this one times the whole matrix, so that's this one right here, the second entry. But since we're adding 3.2, then we can just add the plus 3.2 times 1. Okay, so it's a shortcut. You just add the bias as an extra column to the weight matrix, and then add a 1 here to the input, so that you can just do one matrix multiplication and everything should work out. The math should work out correctly. Okay, so that is the bias trick. Now we also need to be aware of the softmax activation. What is this? This would be the output layer's activation function. Okay, so when we reach the output layer, we usually add a softmax activation on top of it, because since we're doing matrix multiplications, there will be a bunch of numbers, right? So the final number vector in the output layer will be converted into a probability vector. Okay, so you're kind of normalizing the output values into probabilities. So how does that look like? So it would look something like this. So the input image, for example, will be passed to the neural network layers, and then the final output would be some numbers like 3.2, 1.3, 0.2, 0.8. You will pass this to the softmax activation to convert these numbers here, okay, into probabilities, which all sum up to 1. Okay, so why are we computing probability? So we'll learn more about why in a while. But one thing that we could do maybe is just output like dog, because that is the one with, we can just do max here, not softmax, right? Like which one is the max value here? So maybe maybe I can instead of softmax, I can do a max or an argmax, right, of the values here, 3.2, 1.3, 0.2, and 0.8. So which one is the largest? It's 3.2, which is index 0. So I'll just output index 0. That is fine too, but as we'll learn later on, it's much better to produce probabilities, which tells you the confidence of your model that this answer is, let's say 77.5 sure that this is a dog. I'm only 11.6% sure that this is a cat, 3.9% sure that it's a horse, and 7% sure that this is a cheetah, something like that. Okay, so by outputting probabilities, it tells you the confidence of your model, because if you only output like the final answer, then you wouldn't know whether was the model actually 99% sure, or was it 50-50, but it just came out on top. Okay, so that's why softmax activation is important. Okay, so we'll convert the numbers here into a bunch of probabilities, okay, using this equation right here. Okay, so that is how we will use the neural network model using forward propagation. So we'll do a bunch of matrix multiplications from the input, and then we'll multiply it with a weight matrix, then produce the output, and then that output will be used as the input for the next layer, and then finally at the output layer, the last layer, will convert the numbers or the vector to output probabilities using the softmax activation. So next, let's take a look at how the neural network learns during training. So what do we need for the training of a neural network? First, we need a weight initializer. So what is a weight initializer? So it's used to initialize weights randomly, because of course we need to start with some weight values, right? If we start with all zeros, then it's not a good idea, because if all our weights would be 0, then when we do matrix multiplications, the output would always be 0, right? So it would not be useful. So it would be a good idea to just initialize some random numbers for the weights. And some examples of weight initializers could be drawing randomly from a uniform distribution, or a normal or Gaussian distribution. And then there are also specialized weight initializer algorithms like the Xavier and the He initializers. So it turns out through research they found out that when weights have high variance, or so they vary too much, the neural network learns slowly. But if there are the weights also have low variance, it's the same thing. The neural network also learns slowly. So if it's too varied, or if it's too similar, low variance, then the neural network will learn slowly. So what they want is to have the weights variance to be almost 1 for all layers. So that is the goal. So because of this, we have the Xavier initialization method created by Xavier Glorot. So what he did was he took into account the number of connections that are coming in for the neuron, and the number of connections that are coming out also for the neuron, and that would be considered in the initialization of the weights. And he did this for networks with hyperbolic tangent activation function, and it worked pretty well. But it turns out it's not as good for when we use ReLU activations. So Kai-Ming He adjusted the Xavier initialization, so it's kind of similar. It just tweaked some things a bit for it to work on the ReLU activation functions. So they don't just use random weights from some distribution like uniform or normal distribution. They actually consider the number of nodes that are, or connections that are coming in and going out. So fan in and fan out. So yeah, those are some weight initializers that you need to know. Next, we need to set the learning rate. So the learning rate is also known as the step size or the alpha. And the learning rate will control the amount of the weight update. So by how much do we update the weights in training? So since we are trying to figure out the correct weights, of course we will need to update the weights, right? We need to either make it bigger or smaller, but by how much? So this is controlled by the learning rate. So it's usually a small value between 0 and 1, and the usual learning rate that we use are 0.1 and 0.01. Now it's important to set the proper learning rate, because if the learning rate is too small, then the weight updates would also be small, and it would take a long time to train, because our progress is basically small also, because we're doing small updates to the weights. But if you also make the learning rate too big, then our model could jump from one form to another, and it could overshoot the minimum goal, as we'll see in a while. So we will see this later in the gradient descent part of the lecture, the effect of having too small or too big learning rates. But for now, just know that the learning rate is the one that controls the amount of the weight update. Now we might also want to decay the learning rate as we go through training. So What this means is we slowly reduce or lower the learning rate over time. Okay, and the idea for this is because at the start we want big steps, because anyway we started with random weights, so that random set of weights is practically uh, a bad model, right? So we want big steps to update it quickly, okay, or to update it by a lot. But as we go through training and as our model learns some stuff, okay, we might want to lower the learning rate also, and towards the end we're already fine tuning it, so our updates to the weight should just be small and not too big, because if we alter it too much, then it might undo some of the learnings that we had. Okay, so we want to reduce the learning rate over time using learning rate decay. So this helps in optimization and in generalization. Okay, so we usually schedule the learning rate decay in terms of epochs. I mentioned this term earlier, but an epoch is defined as one pass of the whole training set. So meaning the classifier has seen the whole training set already. Okay, so the duration that it took to see the whole training set is one epoch. Okay, so if you have 10 epochs, that means that you have seen the whole training set 10 times. Okay, so we schedule the learning rate decay around the number of epochs. So examples of learning rate decay techniques could be step decay, exponential decay, and manual decay. So for step decay, we could lower the epoch by a certain factor, not the epoch, we could lower the learning rate by a certain factor every certain number of epochs. So let's say lower it by half every 10 epochs or something, or 100 epochs. And for exponential, it's much more drastic. Okay, so you have an exponential lowering of the learning rate over time. Okay, and then for manual decay, this is when you stop the training manually and then change it from, let's say, from 0.1, you manually change it to 0.01. So I've actually experienced this type of learning rate decay because I manually stopped and continued my training when I was doing some neural network stuff before. Okay, so you can also do that, manual decay. Okay, next we also need some regularization techniques, and these are used to reduce overfitting. So in the previous video, we were introduced to the overfitting problem, wherein if your model is overfitting, it's not generalizing to unseen data. It's basically just memorizing what it sees in training. Okay, so it's doing very well in the training set, but it's not generalizing to data that it hasn't seen before. So that is overfitting. So we want to avoid this because we want a general model and not something that just memorizes what it sees during training, right? And because the neural network has a lot of parameters, then it becomes more prone to overfitting. So if you remember from last time, if we have a line, then it's just a very simple model. So maybe we are underfitting. And then if we have like a curve with like 2 parameters, then maybe it's like the good fit. But if we have like a higher order function with maybe 6 terms already, it becomes a very complicated curve, and we're probably overfitting already, right? So if you have a lot of parameters, then you're prone to overfitting, and neural networks are susceptible to that because of the millions of parameters that it could have, right? So we need to employ some regularization techniques, and I'll mention 3 here. The first being dropout. So dropout is what you do when you try to ignore some random neurons during training. Okay, so what this means is if this layer is you apply dropout to it during training, it will pick some random neurons and turn them off. Okay, and why would we do that? Because you want to force the neural network to learn more robust features from different combinations of neurons and not over rely on some just one neuron or 2 neurons. So in the case that those neurons becomes ignored or dropped out, then the neural network will be forced to look for other alternative features. Okay, so usually we choose the dropout rate ranging from 0.2 to 0.5, meaning 20% of the nodes to 50% of the nodes would be dropped out. Okay, so it looks something like this. So maybe this is your standard neural network, and then you apply dropout. So during training, maybe this x'd out nodes would be turned off, so they won't be used during training at during that iteration only. But then in the next iteration, they'll be reset, and then another set of nodes will be turned off. Okay, so why would we do this? Because it forces the network to have redundant representation. So maybe your features for a cat would be it has an ear, it has a tail, it's furry, it has claws, and it has a mischievous look. But what if your classifier is relying too much on the features that it has an ear and it's furry, right? So by doing dropout, and maybe we randomly remove or drop out the ear and the furry feature, then we're forced to look for another way to figure out that this is a cat. Okay, so it's not over reliant on just one or two features. Okay, so yeah, that's the purpose of dropout, and it's quite effective. Okay, the next regularization technique is called L1 regularization, and what this does is it will try to shrink the weights towards 0. So a lot of the weights will become 0, so the weight vector becomes sparse, meaning there's only a few like positive numbers, and a lot of them are 0. So in a way, this is a form of feature selection, because if you have a lot of 0 weights, then that means that you are removing them as features, and then you focus on a few select features that have this positive weights. Okay, so it's a form of feature selection also, and it's called L1 regularization because we penalize the sum of absolute value of the weights. So if you take the absolute value, that's L1 distance. So yeah, that's why it's L1 regularization. And then of course there's also L2 regularization, but what this does is it tries to force the weights to be small but not exactly 0. Okay, so in L1 we want it to we want most of the weights to be 0. We want the weight vector to be sparse, but here we don't want that. What we want is for the neural network to use a little of all inputs, we call that diffuse, and not a lot of some inputs, or peaky. Okay, so what do you mean by this exactly? So what we want is a little of all inputs, so meaning something like maybe the weights would be 0.25, 0.1, 0.03, and maybe 15, something like that. So some weights could be small, but at least you're using all of them, right? Little of all inputs. Whereas what we don't want is a lot of some. So meaning maybe this one is 0, this one is 0.8, this one is 0.001, and then this one is 0 again. So you're only using a lot of the second feature, like you're over relying on the second feature. We don't want that. So it encourages the neural network to have weights that are like, even if it's only small, but you're at least using a little bit of all the inputs. Okay, versus the peaky version, which is overly relying on some features only. Okay, so yeah, that's what L2 regularization wants. So it's called L2 because it penalizes the sum of squares of the weights. So L2 distance, so sum of squares. Okay, so those are the regularization techniques that you can apply for your neural network to avoid overfitting. Okay, the next one that we'll need for our training of the neural network is something called the loss function, also known as the cost function or error function. So what does this do? So the loss function tries to measure how good your model currently is. Okay, so it will boil down to a single number, like an indication of how good your model is, and during training you can monitor the loss function to see if your neural network is actually improving or not. Okay, if the loss function is going down, then that means that you are improving because your error is going down. But if it's not improving, like it's flatlining, or if it's already going up, then that's a bad idea. I mean, that's bad news, right? So you're probably doing something wrong. Okay, so formally, what the loss function does is it measures how much the predicted labels and the true labels vary. Okay, how much does your answers and the correct answers, okay, how much do they vary? So that is what the loss function computes. Now, if you have L1 and L2 regularization applied, you add those terms in the loss function as well, okay, for them to be considered. Okay, so the loss function will try to determine the distance, or how much determine how far off are you from the correct answer, right? So based on the loss function, we could notice that the model on the left is has a higher loss than the model on the right, because the total distance of the correct answer from the model, which is the blue line here, so the total of those distances right here, it's bigger compared to the total distances for the model on the right, which is kind of small only, right? Because they're quite near the model, which is the blue line here. Okay, so the one on the right is much better. So we'll mention two examples of loss function, starting with the first one, mean squared error. So for mean squared error, the loss is computed as follows. So you have the true label minus the predicted label, and then you square that one. Okay, so the true label is the correct answer, the predicted label is what your model produced, and then you take their difference and then you square it. Okay, so and then you do this for all the labels, okay, the predicted labels, and then you take the average. So the average of the squared error is the mean squared error, also known as the L2 loss. Okay, so the reason why we square is we want to make the error a positive value. Why is that? Because let's say that our true label is, let's say, 1, and our predicted label is also 1, right? So 1 minus 1 squared is 0. So there is 0 loss because we were correct. Okay, now if it was 0 minus 0, it's also 0 because it's correct, right? But what if it was 1, the true label is 1, but you had a predicted label of 0? So this would be 1 minus 0 is 1 squared, so 1. But what if it is 0 minus 1? So the true label is 0, but you predicted 1. Now, if you only have this as negative 1, okay, and you don't square it, then you have a negative error, which is which kind of makes the math work differently, or make the math wrong, because we're trying to add up the error, okay? And if you have negative errors, then it will kind of wrongly set the error back when it's supposed to keep on adding the error up, right? So for example, you have an error of 1, and then error of 1, error of 0, and then you have an error of negative 1, then this will kind of cancel out this error of 1 here, when in fact you have 3 errors. So it's supposed to be error of 3, but if you sum this up without with this negative error, then it becomes error of 1, which is wrong, right? So we want a positive value for the error. That's why we do the squaring. Okay, so if we square this, this becomes 1. Okay, so that is why we square. But the other reason is because we want to amplify the big errors and minimize the small errors, so that we can focus on the important errors. So if we square a big number, like let's say 4, 4 squared, it becomes 16. So it amplifies the big errors. And if it's a small error, like let's say 0.01, and if we square that, then it becomes much smaller. Okay, so it allows us to focus on the more important errors and kind of brush off the slight errors that we can just ignore. Okay, so mean squared error is usually used for regression problems. So we'll introduce another one later on, another loss function for classification problems. There is also another one called L loss, which is the average of the absolute value of the error. So we don't square the error, we just take the absolute value. So that also makes the error positive, but it doesn't amplify the big errors or minimize the small errors. So most of the time we use mean squared error over the mean average error. Okay, so this is also possible, but mean squared error is much more preferred. Okay, because of this property that it focuses on important errors by amplifying big errors and minimizing small errors. Okay, so that is mean squared error used for regression. Now, since we are focused on the classification problem, we need another loss function, and this is the cross entropy loss, also known as log loss. Okay, so what does this do? So this is used for classification problems, which is what we're interested in. And we usually pair this with the Softmax activation. So remember from earlier, the Softmax converts numbers to probabilities, right? So those probabilities would be used for the cross entropy loss. And how does it do that? Well, the predicted class probabilities are penalized based on the distance from expected value. So that is why we need to use softmax, because usually softmax and cross entropy comes hand in hand for classification problems. Okay, so I'll show you an example of how to do it exactly in the next slide. But the neat trick for cross entropy loss is, since we're dealing with probabilities, so that those are usually small numbers, so if we are combining probabilities, like instead of multiplying them, we apply the log of the probability so that we can use the sum, because log has this nice property wherein log of so log of AB is just log of A plus log of B, right? So instead of doing a product of AB, you take the log so that you can just have the log of A and then add it to the log of B. Okay, especially since we're dealing with probabilities which could become like really small numbers later on. So we don't want that, because if we multiply a small number with another small number, it becomes really small. So it might vanish eventually, the value, right? So applying log will kind of remedy that problem. Okay, so let me show you how cross entropy loss works. So let's say that we have four classes, right? So we have class A, class B, class C, and class D. Now this is let's say that this is the output for our softmax. Okay, so these are already probabilities that we have. Now our true label is A, and what we do, instead of just having like A, well, we can encode this using something called the one-hot encoding. So for one-hot encoding, we will since our output here is a 4x1 vector, right? 4x1 vector. Our one-hot encoding is also a 4x1 vector where everything is 0 except for where the true label is. So if the true label is A, then our one-hot encoding is 1 0 0 0. If our true label is B, our one-hot encoding is like this. If it's C, then of course it's 0 0 1 0 and so on. Okay, so you get the point, right? So you put 1 where the correct answer is supposed to be, and then 0 for the rest. Okay, so that's called one-hot encoding. And the reason for that is so we could multiply or like compare them directly, the output vector and the true label vector. Okay, so for cross entropy, what we'll do is, okay, so let's clear screen first. So these are the probabilities, right? So it's probability of A, B, C, and D, and then we'll multiply it with what is the correct answer. So the log, and then we'll take the log of the probabilities as I mentioned earlier, so that we could sum up everything. So log of 0.775 is this one, negative 3677. Then we multiply it by 1, so we have this value. But then the rest will be multiplied by 0 anyways, so we don't need to compute this one. Okay, so it's just this one value here. Okay, this one value, log of 0.775, which is negative 0.3677, and then since we have the extra negative here, then it becomes the loss is 0.3677. Okay, so if it's perfectly correct, like let's say this is already 100%, then the loss would be 0. Okay, now you'll notice that for cross entropy loss, it really only focuses on the probability that you assigned to the correct answer, right? So you'll notice that it only focused on this probability here, which is what is needed for the correct answer. Now, whatever probabilities that you set for the rest, which is not the answer, it doesn't care. Okay, because anyway, you did not answer that one anyway, right? So it only is concerned with the probability that you assigned for your final answer. Now, if this was a really small number, like let's say let's say that this was the 0.039 and this was the 0.775. Okay, let's say that these two were interchanged. Okay, so this would have a bigger loss because you assigned like a small probability for the correct answer. Okay, so this will have a bigger loss. So that is how cross entropy loss works. So given the probabilities, you get their log, and then you compute the log of the probability of the correct answer, and then you take the negative of that, and that is your cross entropy loss. Okay, so yeah. Okay, so now that we are familiar with loss functions, we can now try to find the best model by doing optimization using the gradient descent algorithm. So the gradient descent is an iterative and optimization algorithm. So iterative meaning it iterates for a lot of times, right? And what it will do is it will try to find the local minimum of a function. Okay, so the function that we're trying to minimize, of course, is the loss function. So if we minimize the loss function, we'll get the best model. So the goal is to find the model with the lowest error or the lowest loss. Okay, so that is why we'll use gradient descent. So gradient descent will look a little something like this. So let's say that this is your initial weights. Okay, this is your model right now with the initial set of weights, and we adjust the model per iteration, right? So you step in some direction, so you adjust the model, and then it will have a lower cost, and then adjust the model again, and then it will have a lower cost hopefully, and then adjust the model again, lower cost, and until such time that it will find the point wherein it will have the minimum cost already, and it cannot improve anymore. Okay, so that is the goal anyway, is to reach this point here that has the minimum cost. But what we're doing for the gradient descent is we're trying to find this gradient here, which is the slope of the line. Okay, so the gradient is the slope of the loss function. So we're trying to find the direction that the loss function slopes downward the most if we update the weights. So for example, going back here, we're trying to figure out how should I update this set of weights so that if I update them, the loss function will go down the most. Okay, so determine the weight updates such that the loss function goes down by the most amount. Okay, so that's what we're trying to find in gradient descent. And we do that by computing the first derivative of the loss function with respect to the weights and the biases. Okay, so first derivative from calculus, so you're familiar with this already. So this is the like the basic version of gradient descent. So first you choose the starting point, and you do this using the random weight initialization, right? So that is your starting point. Next, you will calculate the gradient using the derivatives. So the gradient is the slope or the direction. So which way should I go? Okay, should I increase the weights? Should I decrease the weights? And so on. Okay, so calculate the gradient using the derivatives, as I mentioned, derivative of the loss function with respect to the weights. And then after finding the gradient, then we will update the weights using the gradient and the learning rate. So the gradient will only determine the direction, the learning rate will scale that amount. Okay, and then we will repeat steps 2 and 3 until we've either reached the maximum number of iterations that we set. So maybe after 10,000 iterations or 100,000 iterations, depending on how much time you have or how patient you are, then we could stop the training. Or if it already converged, meaning it doesn't improve anymore, the loss function does not improve anymore, so meaning we've converged to the minimum already. Okay, so if it has already converged, then we can stop even if we haven't reached the max iterations already, because we cannot improve it no longer. Okay, so that is the basic steps for gradient descent. Now, we said that we want to calculate the gradient of the loss function with respect to the weights. But how do we actually do that? Because the weights are distributed to in different layers, right? So you have weights in the first layer, the second layer, and so on. So you cannot just calculate the whole gradient of the weights like once or in one computation. Okay, so how do we do this if the weights are distributed in different layers? Well, the answer to that is backpropagation. So the idea is we will feed the error backwards, okay, to adjust the weights. So we will start with the final layer. I'll tell you that, hey, this is the error, compute your gradient, and then pass it backwards. And then the second to the last layer will compute its gradient, and then, okay, I have my gradient now, I'll pass this error backwards, and so on until it reaches the first layer. Okay, so you're feeding the error backwards to adjust the weights. So as I mentioned, you first compute the gradient of the loss function with respect to the final layer. So this is where you'll start. So that's derivative of the loss function with respect to the weights at the last layer. So let's say W sub n. Okay, and then we'll propagate this loss backwards to process the previous layers. Okay, so that is the idea for backpropagation. Okay, so this is possible because of the chain rule for derivatives. Okay, so if you recall from your calculus, the chain rule, you kind of decompose the derivative as the product of individual functional parts. Okay, so let me show you an illustration. So let's say that the loss, so we have the loss here. So the loss, if we compute the derivative of the loss with respect to z, the weights z here, we can do that because we have the loss here and then the weights z here. So maybe we have the derivative of the loss with respect to z, and then what we want also is the derivative of the loss with respect to the weights x here and the derivative of the loss with respect to the weights y. But we only have this derivative of the loss with respect to z. How will we incorporate that with in finding these two? So we can actually use chain rule. We can compute the local gradient of derivative of z with respect to x, because we have the z here and you have the x here. So since they're connected, then we can compute this local gradient. And then the same for derivative of z with respect to y, because you have the z here, z weights, and the y weights here, right? So you can compute these local gradients, and so we can now use the chain rule. So for the derivative of L with respect to x, we can have the derivative of L with respect to z, which is this one, the one that we're feeding backwards, okay? And the local gradient derivative of z with respect to x, okay? And because if we remove that, we basically have the derivative of L with respect to x, which is based on the chain rule. And then similarly, we have the same thing for the one at the bottom. So derivative of the loss with respect to y would be equal to this one that we pass backwards. So derivative of L with respect to z times the local gradient derivative of z with respect to y. So remove that, it would be dl over dy, right? So it's all possible because of the chain rule. Okay, so let me show you a more concrete example in the next slide. Okay, so what happens in the forward propagation and in the back propagation? So for the first, what we do is, of course, we feed forward first, right? So the direction is from here going to here. So this is the forward propagation, right? And we're just doing a bunch of matrix multiplications, and then at the end it produced an output. So maybe so let's say 0.53, and then 0.25, and then what else is left? 25, 20. Ano? Wait lang. So 53, 78, yeah, 22 maybe. Tama ba? Yeah. Okay. So maybe those are the final like probabilities, and then the one hot encoding, the correct answer is supposed to be like this, right? So we'll compute the loss here. So we get the loss. So now we want to update the weights based on the loss that we have here. Okay, so we want so we have three sets of weights, right? So we have the weight 1 here, weight 2 here in the from the hidden layer 1 to hidden layer 2. So weight 2 here, and then weight 3 would be from hidden layer to output layer. Okay, so those are the set of weights that we need to update, right? So we want the derivative of the loss with respect to W3. We also want the derivative of the loss with respect to W2, and derivative of the loss with respect to W1. Okay, so those are the gradients that we want. Okay, so first we'll start at the last layer. So the loss here, so we have the loss, and we have W3 here. So we can take the derivative of the loss with respect to W3 directly. So this is possible, this is doable. Okay, so we have this gradient, and now we will feed this backwards. Before that, we need to compute some local gradients, right? So here we will I can maybe use this one, or maybe orange. So from here to here, okay, we can compute the derivative of W3 with respect to W2, since the weight 2 and weight 3 are connected anyway, right? So they're successive. So we can compute this local gradient, And then we'll do the same for the previous layer. Maybe I'll use purple. So from here to here, that would be the derivative of W2 over with respect to weight 1. Okay, so now we can compute the other gradients. Okay, so for this one here, derivative of the loss with respect to weight 2, we can use derivative of loss with respect to weight 3 and multiply that with the local gradient, which was this one, W3 W2, which was this one, right? And then this one was fed from here. So if this one cancels out, that is derivative of L W2, right? And then for this one, this would become d of L dW2 and then dW2 with respect to dW1, which is the local gradient here, and then the first term was fed backwards from the previous layer. Okay, so we now have computed the three gradients: loss with respect to weight 1, gradient the loss with respect to weight 2, and loss with respect to weight 3. So now that we have these three gradients, we will pair them up with our learning rate to update the weights here. So this is the, I'll call this gradient 1, I'll call this gradient 2, and I'll call this gradient 3. And to update the weights, we will just have learning rate times gradient 3, and then for weight 2 we have learning rate times gradient 2 and learning rate times gradient 1. Okay, so we compute those gradients and then pair them up with the learning rate to update the weights. Okay, so that is how backpropagation works. So we can compute the individual gradients of each weight in different layers by passing the error backwards and using chain rule to use the previous information together with the local gradient to compute the gradient for that layer. Okay, so that's it for backpropagation. Okay, so let me remove everything. Okay, now we have to be careful with gradient descent because it's kind of susceptible to settling down in local minima. Okay, so what we're trying to find is the global minimum, but sometimes it gets stuck in local minima. Like for example, in this one we have three minima. This one, the first one is the global, right? And then these two are local minima. So if you start, let's say your weights start here, and if it goes down, it can only converge to this local minima and not the global minima, because once we get once we find the minimum, we don't move anymore, right? Because we've converged. Okay, so it does get stuck at local minima, which is kind of a problem. And I mentioned earlier that learning rate is important in gradient descent, and this is what happens. So if you have a small learning rate, then your progress would be really small, because we mentioned that the learning rate is used to update the weights, right? So the changes in your weights would be really small if you have a small learning rate. So your updates would also be you would also be moving slowly towards the minimum. But if you have a big learning rate, then you might jump from here up to here, up to here, up to here, and then you might overshoot the minimum, so you might not reach it. Okay, so be careful about setting your learning rate. So we have concrete examples here. So for example, you have a really this is the smallest one, 0.1. So it converged eventually to the minimum, but it took 24 iterations. Okay, when you only when you used a slightly bigger learning rate, which is 0.3, then it jumped from here all the way down here, and then it converged in only 8 iterations. So it converged faster, right? And it even reached a better loss function. And then for the the big learning rate 0.8, then maybe you jump from here and then to here and then to here and then to here, and then it might not be stable, right? Same with 0.9, right? You might eventually reach it, but especially with if you use learning rate decay, but you do a lot of unstable jumping around if you have a big learning rate, because you are changing the weights too much. Okay, so that is the effect of your learning rate. Now, gradient descent actually has 3 different flavors or 3 different types. So let's start with the most common one, which is stochastic gradient descent, or SGD. So in stochastic gradient descent, we update the weights after computing the error for one training sample. So each time we see a training example, we compute the error and then do the back propagation, update the weights. Okay, so we do that for each training sample. So if you have, let's say, 10,000 training samples, then you'll do the update 10,000 times in one epoch. So because of the frequent updates, there's a detailed rate of improvement, and sometimes it leads to faster learning. But the problem is, this is computationally expensive because you're doing weight update for each training sample. And of course, if you have a really large training set, then you would have to do a lot of computations, right? So if you do this, the error rate can also fluctuate because maybe one training sample is very different from the next one and then the next one. So it could change the weights drastically based on the error, and so the error rate can fluctuate. Okay, and because of noisy updates, there could be a harder time for the algorithm to converge, right? So it might take too long sometimes, okay, especially because of the noise. Okay, so for example, you're already on the right track, and then one bad training sample kind of like puts you in the wrong direction, so it kind of undoes what you've learned so far. So because of this kind of noise, then sometimes it's hard to converge using stochastic gradient descent. Now the opposite of this is something called batch gradient descent, wherein you only update the weights after computing the error for the whole training set. So you look at the each training sample, but you compute their errors, but then you just compile them, and then once you have already looked at the whole training set, that is when you compute the error and that is when you update the weight, because you've been computing the error as you're going through each training sample, right? So you do the update once after seeing the whole training set. So it's computationally more efficient than stochastic gradient descent because you're not doing as many updates, and it also provides a stable convergence because you're doing updates at a steady manner and not like at each sample. However, the problem is it's susceptible to premature convergence. So meaning it converges to a local optimum, which is suboptimal. Okay, so it could stop at a point wherein the model is not yet optimal. Okay, you can still do better, but since you're doing the update of the weights too long, then it has already stopped learning, basically. Okay, and of course, if you have a large data set, then the training would be too slow because you have to wait for the whole training set to finish before doing the update. Okay, so you will have a really slow progress in training. Okay, so that is the first two, and the third one is a combination of stochastic and batch gradient descent, and that is the mini batch gradient descent. So what you do is, instead of looking at it, instead of doing updates for each sample or doing the updates after you've looked at everything, what you do is you separate the training set into small batches and you do the update of the weights after each batch. Okay, so it's kind of a compromise between the batch gradient descent, which looks at the whole data set or the whole training set, and the stochastic, which updates each time it sees a sample. Okay, so instead you divide it into batches. So common batch sizes could be 32, 64, 128, and 256. So maybe every 64 samples you update, another 64 samples you update, and so on. Okay, so that is mini batch gradient descent, which is like the best of both worlds for batch and stochastic gradient descent. Okay, so those are the three types of gradient descent. Now, there is also another extension, SGD, or stochastic gradient descent with momentum. So what is momentum? Momentum basically keeps track of the direction of previous weight updates. So you're keeping track of the direction that you've been doing so far. So if you're going upwards, so and you've been doing upwards for a long time now, then if it suddenly if the next weight update wants you to go downward, then you will kind of hesitate, because hey, I've been doing upwards so far and then you're telling me to go down. Then maybe the momentum is stopping you from doing such a drastic change. Okay, so you keep track of the previous weight updates by doing a moving average of the gradients. Okay, so with momentum, you're kind of using a guided direction for your updates. So it will lessen the zigzags. Okay, so jumping from one direction to another, because you are keep making use of the current direction or the current momentum. Okay, and usually leads to faster convergence because you lessen the zigzag, right? So you usually choose the momentum factor from 0.5 to 0.9, meaning that is the amount of weight that you use for the momentum, or the direction of the previous weight updates. Okay. The problem of momentum, however, is that when it's close to the goal and it's still high momentum, it doesn't know that it should slow down because it doesn't know that it's close to the goal. So if it still has high momentum, then it will keep going. Okay, so yeah, so this is how momentum looks like. So without momentum, the convergence could look something like this, a lot of zigzags. But with the momentum, what happens is, let's say that so far the momentum is telling you to go this way. So this is the momentum direction in green. So maybe I should do that in green as well. So if this is the momentum step here, okay, and then your gradient step is telling you to go in this direction, then the momentum is telling you to go up, and then gradient is telling you to go left. So you kind of meet in the middle, and your actual step would be something in between of them. Okay, so yeah, so you have the momentum step here, and then the actual step is actually somewhere in the middle, because you don't go fully to the left, right? But you also don't continue towards just full momentum here, momentum direction, because the gradient is now telling you to go left. So maybe meet somewhere in the middle. So the result would be it has less zigzags, right? So this one has a lot of oscillations, this one has lesser ones with momentum. Okay, so that is momentum. Now there is an alternative to momentum, which is the Nesterov momentum, or the Nesterov accelerated gradient, which solves the problem of momentum, that it doesn't know how to slow down when it's approaching the goal. So this one solves that problem. So the difference is that for momentum, we did this, right? So you're currently at this point, okay? You're currently at this point, and then you compute the momentum step. So this is going in that direction. You compute the gradient step, so it's going in this direction, and then the momentum update will actually be somewhere in between, okay, depending on the momentum factor also. But for Nesterov momentum, what happens is you're at this point, okay, so the momentum step tells us that it should go to this direction, and then at this point, this is when you actually compute the gradient. Okay, so you don't compute the gradient at the original point, you compute the gradient to where the momentum step is telling you it will land, basically, or it will end up in. So you're doing a look ahead gradient because you're computing the gradient after applying the momentum step. So with that, after doing the gradient here, then this is the actual step that we're going to do. Okay, so yeah, just a little bit different with the original momentum, but just by doing this, it will kind of solve the problem of the original momentum. So that's Nesterov momentum. Okay, other optimizers include ADAGRAD, which stands for adaptive gradient, and what this does is, well, it has an adaptive learning rate. Okay, so it doesn't only use a single learning rate value. It actually uses a different learning rate for a different set of for some features, and then a different learning rate for other features. Now, how does it do that? It figures out that for the frequently updated features, you can use a lower learning rate, and for rarely updated features, you can use a higher learning rate. Now, why is that? Because if it's frequently updated, then that means that you've been focusing on this feature a lot, right? So that means that you've probably learned a lot about it already. So you can just use a lower learning rate because you're maybe in the fine-tuning stage regarding that feature. But if it's a feature that's being rarely updated, okay, that means that it's close to the random initial value that you've started with, right? So since you rarely update it, then you need a higher learning rate for that, because it's still close to random, right? So you need to make it jump a little higher, or have a big step to make the change immediate, right? Because if you use a lower learning rate here, then it will not really update the weights too much, or the effect won't be as high. Okay, so that is the idea for ADAGRAD. It will have an adaptive learning rate for based on the frequency of updates on the features. The problem, however, for ADAGRAD is that it's still prone to premature convergence, because in most cases, if you have lowered learning rates for frequent features, then it will stop learning already, and maybe at that point it's not the optimal model yet. Okay, so yeah, that's the problem for ADAGRAD also. Now, another adaptive learning rate technique for optimization is called RMS prop, which stands for root mean squared propagation. So as I mentioned, it also has adaptive learning rate. Now, compared to the stochastic gradient descent, which has huge oscillations, so it has the zigzag patterns, so those are called oscillations, and there's a lot more iterations because of the noisy updates. For RMS prop, it will try to dampen the vertical oscillations and allow larger horizontal steps for you to be able to reach faster convergence. So what does this mean? Meaning, we are trying to limit the vertical zigzags and allow you to jump horizontally much bigger than the normal SGD. So it will give you a higher learning rate if you need to, and it will give you a lower learning rate if you need to. So that's why the learning rate is adaptive. Now, this is a famous optimization algorithm, but it's actually unpublished. This was just mentioned by Geoffrey Hinton in one of his slides in a Coursera course for neural networks. Yeah, so it's famous, but it's not really published. Okay, so for RMS prop, here's a little diagram or an illustration. So for the normal SGD, you have like oscillations up and down here, but then for RMS prop, which is in green, so you limit the vertical oscillation, so it's not as high, the zigzags, and it will allow you also to jump vertically to allow for faster convergence. So you could allow a higher learning rate to jump horizontally, because horizontal means that you are updating the weights by a lot. Okay, so yeah, RMS prop will adaptively adjust the learning rate for you depending on the computation. Next, we also have the ADAM, or the ADAM optimizer, which stands for adaptive momentum. So besides having adaptive momentum, it also has adaptive learning rate. So it kind of combines the RMS prop and momentum. Okay, so it's one of the more popular optimizers these days. So yeah, if you don't know what to use, just use ADAM. Okay, so those are the optimizers that we use to find the best model for our neural networks. Now, when we do the learning process, when we train the neural networks, we have to monitor the loss function, basically, right? So there's a separate loss function for the training set, and there's also a separate loss function for the validation set, because for the training loss is of course evaluated on the training set, the validation loss is evaluated on the validation set. Okay, so usually the loss curve will slope downwards, okay, meaning it's being reduced. So as you train more, the loss should decrease. Okay, now if it's not decreasing anymore, meaning it's flatlining, then it's not learning anymore. So it's reached the limit of the model. Okay, so that is what the model can learn, and it has already stopped learning, so you can stop it right there. And if the loss is already starting to go upwards, then it's also time to stop the training, because you are now overfitting. Okay, especially if it's the validation curve that is going upwards. So usually you have the training loss that's going downwards, and the training loss could still be going downwards because it could end up like memorizing the whole training set, but you have to monitor the validation curve. So the validation curve will also start going downwards, but then at some point it will start to go upwards. So meaning you should have stopped here, right? Because that means that this is already the best model possible, because if you train more, then you're already overfitting, because the validation loss is already starting to go up. So meaning you're memorizing the training without generalizing to unseen data. Okay, so you can stop early based on the loss curves. So you need to monitor the loss curve. It will look something like this. Okay, it's really noisy, but the curve is still kind of apparent. And on the other hand, we have the result of different learning rates to the loss curve. So if you have a high learning rate like the green one, so at this point you can drop like steeply, so it has a huge improvement right away, but then it kind of tends to flatten out already, so it stops learning. Okay, so there's a big drop and then it stops learning. So at this point, this is the loss of the model. It's not the best, because you could have gone even lower than that, and that is the effect of having a high learning rate. So at the start, you had the random weights. Since you have a high learning rate, you added you updated it quickly, so it became better. But since you still have a high learning rate, it did not improve anymore. Okay, so it flatlines. Now if you have a low learning rate naman, it will go down, but at a really slow pace. Okay, so eventually it will go down, but it's really slow. Okay, so you need to find the good learning rate, so just the right amount, so that it will go down and it will do so at a faster pace than the low learning rate. Okay, and you also don't want it to be high enough that it flatlines early. So you want it to be as close to zero as possible, the loss, okay, before it starts flatlining. Okay, now if you have a very high learning rate, then this could happen. Like it could go down and then go overfit right away, or yeah. So that's bad. So try to avoid that one. Now you can also monitor the accuracy, which is the the percentage of correct answers, and you can plot the training accuracy and the validation accuracy. So training accuracy again is evaluated on the training set. Validation accuracy is of course on the validation set. So if you notice that there is a big gap in the training curve, the training accuracy and the validation accuracy, that probably means that you're overfitting already, because you have a higher accuracy in the training set, but the accuracy in the validation set remains the same. Okay, so it's a sign that you're probably overfitting already. Now, if there is no gap, meaning it's flatlining, then that means that the model has reached its capacity, meaning it's not learning anymore. So maybe you try to increase the depth, maybe make the neural network more complex, so that it could have a higher power or model capacity. Okay, so you could make it deeper, add more neurons, and so on. If you see that it's already flatlining right away. Okay, so you can also do that to check if you need to stop early and maybe retrain or redo the parameters, because there's nothing worse than like waiting for 10 hours for the training to stop and then only to end up with a really bad model, which you could have avoided just by looking at the graph or the plot and see that, well, it's not learning anymore, right? I shouldn't have to wait for 10 hours to stop this nonsense already and just redo. Okay, so yeah, you need to monitor the learning process so that you don't waste time and you can stop early or regroup and retrain. Okay, so that's babysitting the learning process. Now, I also want to talk about the difference between parameters and hyperparameters. So for parameters, or the model parameters, these are what the neural network learns during training. So these are the weights and the biases of the connections and the bias of each node, right? So these are what the neural network learns. So those are parameters. Now how about hyperparameters? These are options that you set before training. Okay, so you've already predetermined this, you've selected this, and you as the network designer chose this before training. Okay, so parameters, they are variables for the model, they are learned during training. Hyperparameters are variables for training and they are set before training. Okay, so those are that's the difference. So what are some of the hyperparameters for our neural networks? So it could involve it could be hyperparameters that involve the network architecture, like for example the architecture itself. So how many neurons, how many layers, that is something that you set beforehand. Okay, you as the network designer will decide how many neurons should I put in this layer, how many layers should I go. So should I only have 2 hidden layers, 3, 5, 10, and so on. So that will make up your architecture. Okay, next, what activation functions should you use? Should you use ReLU, sigmoid, hyperbolic tangent, and so on? Okay, that's also another choice. Should you use dropout? What is the dropout rate? So that is also part of the network architecture. Then of course there are the training parameters, or the training hyperparameters, sorry. So example would be the choice of weight initializer. So would it have been better if we used the Savior initialization instead of just having uniform distribution? Okay, so you can try it out and see if that hyperparameter is better, right? Or would I have had a better model if I used a different optimizer? So instead of SGD, I used ADAM or ADAGRAD or RMS prop. Okay, so the choice of optimizer is another hyperparameter. Next is the learning rate. So you chose this beforehand. So 0.1 or 0.01 or something else, and then of course the choice of learning rate decay as well. That's another hyperparameter. And then should I use momentum, and what is the momentum factor? That is another hyperparameter. And then if you're using mini batch gradient descent, what should be the batch size? Would it have been better if I used 64 instead of 32 as the batch size, or maybe 128, or even a bigger batch size? Okay, so you can check if you want to. And then of course you need to set the number of epochs, okay, or the number of iterations that you need to see the training set. So it could be 1,000 epochs, 10,000, 100,000, million epochs. So it all depends on the time that you have, the patience, and of course the computing resources that you have. Okay, so of course the longer you train in general, the better your model is supposed to be. But at some point it will reach to the point of convergence that you can stop early. You don't need to reach 100,000 iterations to reach your best model. Maybe if it has already converged, then you can already stop, right? But these are the hyperparameters that you can set for your training. So these are set beforehand. You already decided before training that, hey, I will use Xavier, I will use Adam, I will use the learning rate 0.01, I won't use momentum, I will use batch size 64, and then I will run this for 1,000 epochs. So those are all pre-decided before training, so those are all hyperparameters. Okay, but since these are still some items that you need to tweak or you need to decide on, how do you know what are the optimal hyperparameters? So one way to do that is by doing grid search. So it's basically exhaustive search or brute force. So you try all combinations. Okay, so if you have like two hyperparameters that you're not sure of what the best options are, then you try all possible combinations. Or you can also do random search, wherein you randomly sample hyperparameters based on their distribution and based on the probability distribution, and then you can just pick out some samples. Okay, so for grid search, you need to try all possibilities. For random search, you just need to randomly sample hyperparameters based on their probability distribution. Okay, so maybe you want the learning rate 0.01 to appear 80% of the time and 0.1 only 20% of the time. So you can do something like that. So grid search would look something like this for hyperparameter tuning. So maybe you're not sure what the best learning rate is and what the maximum depth of your architecture is. So you can try everything. So your choices could be 0.001, 0.01, and then 0.05 for the learning rate. And then for maximum depth, you have 4, 6, and then 8. So you try all possibilities. So 4 and 001, 4 and 001, 4 and 05, and so on. So you try all 9 possibilities. Okay, so it takes a lot of time, of course, because you will have to train one model using this set of parameters, hyperparameters, and then after that you need to train it again using this set of hyperparameters, and so on. So you'll have to train it 9 times and then compare the models that you have, okay, and then figure out which one has the best performance, and then you'll use that final set of hyperparameters. Okay, so that is how you find your optimal hyperparameters. You just need to grid search or try some combinations. Okay, so that is how you train the neural network, and then how you optimize your hyperparameters. Okay, next let us look at something called the deep learning. Of course, you've probably heard of it already. And the difference is that well, it's just the number of hidden layers. Okay, so if this is a neural network and this is a deep neural network, the only difference is that this has more hidden layers. So if you're a deep neural network, you have more than 2 hidden layers. There is no exact number for what qualifies as deep, but that's the general rule of thumb. If you have more than 2 hidden layers, then you're already considered a deep neural network. Okay? For deep learning, we're actually really referring to the depth of the neural network and the complexity of the architecture. Because as we'll see later on, there could be some deep neural nets that have really complex architectures. Okay? So deep learning is state of the art for many tasks in machine learning, in computer vision, in natural language processing, and in general for artificial intelligence. So let's take a look at some of these applications of deep learning. So number one, of course, self-driving cars. So it's used in processing the camera sensor. So what it sees on the road, are there pedestrians along the way? So you have convnets for that one, and then of course the decision making of what to do, whether to steer the wheel this way or to hit the brakes and so on. So self-driving cars are powered by deep learning. Okay. You can also use this for fake news detection. Okay, so given a lot of articles in the Layer dataset, okay, so you can train a deep neural network to detect if this is fake news or not. Okay, and then of course there's a lot of applications in healthcare, ranging from medical imaging, diagnostics, data and patient data analytics. What else? Like virtual assistants related to healthcare and so on. So it's also prevalent in healthcare, and of course just your normal virtual assistants like Siri, Cortana, Alexa, Assistant, Google Assistant. Those use deep learning as well in the speech to text synthesis. So it kind of figures out what you're saying and converts it to text. So deep learning is also involved in that one. Then of course machine translation, translating from one language to another. The Google Translate, for example, used deep learning for that one to because it doesn't just use like a dictionary of words like hello is hola or hello is bonjour. It also how it learned to translate is basically like look at an article in English and then an article in the same article in another language and then figure out the translations from those. Okay, so it used a lot of data and yeah, it used deep learning for machine translation. And then you also have a combination of like image and text. So you have the image text translation. So you can point the camera at this, let's say, image or this box, and then it will figure out that there's some words there. So Mork Chocolate means dark chocolate. So it can automatically translate even if it's an image. So it's a combination of like optical character recognition and then the translation, of course. Okay, and then there's also something called the pixel restoration. So let's say that this is your original image and then you downsampled it to, let's say, 8x8 input. You can actually recreate a 32x32 sample, or you upscale it using deep learning. So I already mentioned this earlier, the super resolution from the generative adversarial networks, or GANs. This is an application of that. You can also do image colorization using deep learning. So you're given a grayscale image and then you can automatically color it using deep learning. Okay, and then you have image description. So you're given an image and then you can deep neural network can describe what is there in the image. So it will describe it using a bunch of tags, like this part here is a bouquet of red flowers, this is a tablet, it's a bottle of water, this is a cup of coffee, and so on. Okay, so it's a description of the image, automatic description. And then the opposite is text to image generation. So this is also another application of GAN. So you're given a text, okay, and then you'll try to produce an image based on the text. So let's say this small bird has a pink breast and crown and black primaries and secondaries, and then it will produce an image based on that description. So it's like the opposite of this one, right? Because it's from image, you get the text describing them, and then from here, the text that describes them, and then you produce the image. Okay, so deep neural networks can also do that one. Of course, it can also play games like Breakout, the classic Breakout game like this. So you can teach a deep neural network to play games. Even it can even play Dota 2. Okay, so OpenAI, which is a company founded by Elon Musk, created an AI for Dota 2, and it actually beat world champions OG. Okay, so they beat good players, human players. Those were two-time world champions, OG, and they were able to beat them. And then, of course, you're probably also familiar with AlphaGo, who beat Go world champion Lee Sedol. So this was also powered by deep learning, and yeah. So Go is thought to be even harder than chess in terms of the search space. So they kind of figured out before that maybe you can't create a bot for it, and then they did it using deep learning. Okay, using the Google DeepMind team. And then of course another one is the robot can learn how to use tools by watching YouTube. Okay, so if you allow it to watch videos unconstrained, maybe it can learn how to do things like use tools. So maybe it can learn how to cook or learn how to chop onions and so on. So this is kind of scary, really, because this is one step closer to robots becoming sentient, but we're probably far from that anyway. Yeah, so those are some cool deep learning applications that you can that already exist nowadays. Okay, so deep learning is really helpful. It can also be fun to apply, and yeah, it's basically just neural networks but on steroids, because you go deep and you have a lot of hidden layers. Okay, so for deep learning to be able to be possible, we need two things. We need tons of training data, so a lot of training data, not just thousands but like millions of training data. And in general, the more training data that we have, the better. Okay, because we can have more examples to feed to our neural network and train it to be more robust, and to be the more that you see the more examples that you see, the more knowledge that you gain basically from training, right? So you need tons of training data, first of all, and second is you need a GPU for faster training. So examples of GPU are shown here. You have the NVIDIA GeForce GTX, and the NVIDIA Titan, NVIDIA Tesla, and others. Okay, why do we need GPU for deep learning training? It's because if you use CPU training, it's too slow and it takes too long. And I actually had experience with this when I was taking a deep learning course before. I didn't have my laptop didn't have CPU. No, not CPU. My laptop didn't have a GPU yet at that time, and so I had to settle for CPU training, and it took me 18 hours to finish the training. And my poor laptop worked non-stop for over a week, and that 18 hours, that's only for one model. I had to train another 18 hours or 16 hours for the second model when I tried something else in the architecture, and then of course another set of hyperparameter check, right? So it really takes too long if you use just plain CPU. So you need GPU for faster training. Okay, so the reason for this, why do we need to use GPUs or the graphics processing unit? It's because for deep neural networks, of course, you have more layers, right? Because it's deep. So more layers means that you have more weights to learn. And so usually you have millions of parameters already. And GPUs are created or they're specialized for image processing because, well, they are called graphics processing unit to process images, right? Or to process graphics. And so, because of this, they are optimized for doing fast and large matrix multiplications and convolutions. So, fast matrix multiplications, that's what we want because in training deep neural networks, we're doing a bunch of matrix multiplications. And convolutions, it's something similar. We'll do that for the convolutional neural networks. So, GPUs are really a good idea for training deep neural networks. And it can also do parallel computation, so it makes the training faster. So thanks to the gaming community, which needed better GPUs, the deep learning community also reap its benefits because we used it for training deep neural networks. Okay, so yeah, that's why we need to use GPUs. Now, if you're planning to do deep learning, of course, there are already frameworks that exist out there. So, some of the more famous ones are TensorFlow, okay, Keras, MXNet, PyTorch, Caffe, the Microsoft Cognitive Toolkit or CNTK, the DL4J, which is in Java, and then ONNX. So, usually the languages that are available for the deep learning frameworks are Python, C++, and Java. So most of these frameworks are available in different languages, but famously TensorFlow is in Python, PyTorch of course is in Python, but Torch is more general, it's language agnostic. Keras is a framework or a library on top of TensorFlow. Then Caffe is the more older one, and then of course you have the DL4J for Java, right? So yeah, so these are some of the deep learning frameworks that you might be interested in using if you want to apply deep learning. Okay, so that is deep learning. Okay, so let us now go to the last part of this video, which is about convolutional neural networks. Previously, when we talked about image classification, we mentioned that there was a huge semantic gap from what the computer sees, which is just a bunch of numbers, to concluding that this is a picture of a cat. Okay, so can we have neural networks that can do image classification with high accuracy? So maybe we're presented with images like this. So is it a dog or a bread or a donut, right? So they kind of look similar. Can our neural network distinguish between these two? Can we distinguish between dogs versus mops? Because they kind of look similar too, right? With those white, long white, I don't know, string-like things. And then you have dogs versus bread again. Okay, they kind of look the same. And you have chihuahuas versus muffins. They also kind of look the same. So can we have a classifier based on neural networks that can distinguish between this with high accuracy? And then of course you also have your cats versus, I think, caramel sundae, I think. Yeah, so they kind of look similar in color and in texture patterns, but can we have our image classifier using neural networks distinguish between the two very well? Okay, turns out we can, and we do that by using convolutional neural networks. So convolutional neural networks, or CNNs, or ConvNets, okay, are neural networks that use convolution filters. And they're mainly used for images, and it's the state of the art in image classification and other computer vision tasks. So in most computer vision tasks, we already use ConvNets for that one. Okay, so why do we use convolutional neural networks? Because for images, it's high dimensional data, right? Because for example, if you have a 1080p image, that already has 2 million pixels. So if your input has 2 million pixels or 2 million parameters, and then you pass that in as each pixel as a neuron, it would be impractical, right? So it's impractical to use each pixel as input, because then you would have 2 million neurons in the first layer, which is already too much. It's only the first layer, and you already have 2 million pixels or 2 million neurons, right? So it's too much. So what we'll do instead is we won't use one pixel one by one, but instead we will look at local windows in the image. So we look at local neighborhoods using filters. Okay, so let's take a look at this simple CNN, for example, that distinguishes between an X and an O. Okay, so if it sees this image, it will tell you that, hey, that's an X. If it sees this image, it tells you that that's an O. Okay, so pretty basic. And it should be able to output X and O even if there's translation, so even if it's not really centered or something, like it's also not centered here. It doesn't have even if it doesn't have the correct scaling. So this one is kind of smaller than the template, and also this one is also slightly smaller. Slight rotation changes, okay, or warping. Okay, so this is not a perfect circle, this is not a perfect X, but still looks like an X, right? So should still be able to classify that as an X. And even if we add more weight, like we dilated the X and the O, it should also be able to classify it still as the X or the O. Okay, so it should be robust, and it should not matter if there's translation, scaling, rotation, or dilation. It should still work. Okay, so a simple template matching will not work for this one, because if we just use template matching, like this is our template of an X, and if we match that with our input image, then it will tell you that, hey, there's a lot of errors in the template matching, so this is probably not an X. Although as humans we can see that this is an X, but for the computer, if it follows a template matching procedure, it sees a lot of errors here, so it will tell you, hey, that's not an X, which is wrong, right? Because this is clearly an X. So instead of doing full template match for the image as a whole, what we'll do instead for convolutional neural networks is we will match parts of the image. Okay, so for example, this left diagonal here is kind of the same as this left diagonal here. This X here is kind of the same as this X here, okay, denoted by the orange box. And then this right diagonal here is the same as this right diagonal here. So we're matching parts of the image and not the image as a whole. Okay, so we're looking at local windows and trying to match them, and if most of them or a lot of them matches, then it's probably the same image, right? So that's the basic idea for convolutional neural networks. Okay, so we will match using filters. Okay, so our filters are like patterns, okay, or features. So for example, we have the left diagonal filter here, you have the X filter here, and you have the right diagonal filter here. And then we will slide that over, or we will align that with some of the blocks here. Since this is a 3x3 filter, all three are 3x3 filters, so they will match in some parts, and then they will not match in some parts, but that's the basic idea. We will match them to local windows, okay, in the image. So convolution filters, or filters for short, or also known as kernels, represent features. So these features could be edges, corners, textures, and so on. So any type of feature that is possible. So those are learned by our features, okay? So they are learned in training. So we put weights inside these filters, which are usually a small window, okay? So maybe 3x3, 5x5, and so on. And those weights are learned during training, so they are what is being adjusted. So we already went through it earlier with neural network training, right? That we learn about the weights and we update them during training. So in convolutional neural networks, the weights in the filters are what's being learned during training. Convolution filters allow us to utilize spatial relationships in the image, and we'll see what this means in a while. And it also allows us to do parameter sharing, because the features can be found anywhere in the image, so we can use the same filter. Now what do we mean by this? So for example, if we're trying to find this flower right here, the filter that I'll use to find this flower is the same as the filter that I'll use if the flower is right here in the bottom right. Okay, so this one is on the top left and this one is on the bottom right, but it should use the same filter because I'm looking for the same thing, right? So it should be shift or translation invariant. Okay, so that allows you to use the same filter because we don't know where the features can be found. Okay, it could be anywhere in the image, so that's why we will slide the filter all throughout the image and try to find these features anywhere in the image. And then when we talked about spatial relations earlier, it just means that we're not looking at the pixels individually. We are looking at them as a group of pixels. That's why we put them in a window, in a 3x3 window, for example, in these three filters here. And by spatial relations, we mean that this pixel here is related to this pixel here and related to this pixel here, forming the diagonal. And then for this filter, we have this 5 pixels being related to each other, forming the cross. And then for this filter, we have this 3 pixels forming the right diagonal. So those are the spatial relations, meaning you're aware that each pixel is related to some pixels in the neighborhood, and you are kind of limiting the space by setting the kernel. Okay, so the size of the kernel, it could be 3x3, 5x5, so that's the size of the neighborhood. And then the filter itself will try to learn the weights, so which pixels in this window should be more or less strongly related. Okay, so for example, this 3 should form like a diagonal, and so on. Okay, so that's what we mean when we say spatial relations in space. Okay, not special as in like special someone, spatial. Okay, so for convolution filters, of course, we need to do the convolution operation, right? So we have the input image, let's say, which is this matrix, and then we have our filter or our kernel, which is like the cross one. Okay, and what we do is we will align it with so this one is a 5x5 input, right? So let me write that down. So this is a 5x5 input, and the kernel size is 3x3. So the filter is smaller, of course. So we will first look at the 3x3 window here, which is somewhere. Okay, so we'll look at this 3x3 window here first. Okay, so what we do is we will align the filter with this window here, 3 by 3 window, and we will multiply the input values with the filter value. So 1 times 1, 1 times 0, and so on. And these are the results. Okay, so you have the 1 here, 1, 1, 1, and then the rest are zeros. Okay, and then you take the sum of everything. Okay, so since there are 4 ones, the sum would be 4. So in the output, which is called the feature map, this part here would have 4. Okay, now on the next window, we move that one here, next 3 by 3 window. Okay, so let me erase everything first to make it clean. In the next 3 by 3 window, we're looking at this part of the input image and do the convolution again with the kernel. So that's 1 times 1, so there's 1 times 0, 1 times 0 is 0, 1 times 0 is 0, then 1 times 1 again, so there's another 1, there's a 0 here, 0 here, and another 1 here. So that is 3. Sum is 3, so we'll have 3 here. Okay, and then do that again for the next window. Okay, so we had 3 earlier, right? So for the next window, we'll do that convolution thing again. So we'll only need to look at this, this, and this, because those are the ones, right? So you have 1, 2, 3, 4 as well. So that's 4 as the sum, and then you do that for each window. After you're done with this window, you move down to the next row. So after that, you look at the next 3 by 3 window, which is somewhere here. Okay, so that's what you do for convolution. You align the filter with small windows in the input image, then you do the convolution, you multiply the aligned values, and then you take the sum, and then that sum is what you output in the feature map. Okay, that's how convolutions work. So for the convolution layer, you're doing convolutions. This is the sign for convolution. So image convolved with the filter produces the feature map, which is the output. Okay, and we do a sliding window. So you slide the filters over the image from left to right, from top to bottom. Okay, just like what we did in the previous slide. So for this one, for example, if this is the filter and then this is the window that we're looking at right now, then it's a perfect match because everything aligns, right? So the sum of this is 9. Okay, so everything is 1 here, so it's 9. And then for this example, it was normalized, divided by 9, so it becomes 1. So it becomes the numbers, or the numbers for the output are normalized so that it becomes they call this from the range -1 to 1. Okay, so we normalize it. And then for if you look at this window, on the other hand, only this parts here match, and then these two parts here don't match, right? So they have a -1. So if you sum that up, that's 7 over 9. It's just 0.55, right? 1, 2, 3, 4, 5, 6, 7. Oh no, 7 minus 2, so that's 5. So sorry, not 7 over 9. 7 minus 2 is 5 over 9, so that's why you have the 0.55 here if you normalize it. So if you apply everything, it would look something like this. Okay, so if you convolve the image with this filter, okay, so if you run it on the 3 by 3 windows, these are the results. And you'll notice that since this is the diagonal filter, right? So it's a diagonal filter, so it had the biggest activations or biggest results somewhere along here, which is exactly the part of the image which has the left diagonal, which is somewhere here. right? So those are the biggest activations in the feature map. Okay, because our filter is looking for the left diagonal. Okay, now if we look at the other filters, okay, so if you look at the results of the other filters, we'll notice that, okay, so this was the one earlier, right? So the left diagonal had this one. So those are the big activations with a 1. And then for the right diagonal, it's the opposite. So it's kind of detecting this one right here. Okay, and then the rest, it has really low values because it doesn't have the right diagonal pattern. So for example, at this window here, it doesn't have the right diagonal pattern, so that's why it has a low number here. And then for the X part, the X pattern, it only really triggers at the center because that's the only one that has the X pattern, right? So that's why you'll notice it only has 1 at the center. Okay, and everywhere else, very low values because, for example, here, it only matches like half of the X pattern because this is like only a right diagonal. It doesn't have the corresponding left diagonal to form the X. Okay, so yeah, that's the idea for convolution. It's you have your input image right here. Okay, so these are the input images. Oh, so these are the input images, and then you convolve them with a filter, and then you produce the feature map. Okay, so yeah, that's the convolution layer. And for convolution filters, they are usually in RGB. Okay, so especially if you have colored images, so there are for one filter, it's usually in 3 channels: the red channel, green channel, and blue channel. So if you apply it on an RGB image, then it would also apply the individual channels for the filter to the appropriate is it on the red, green, and blue. Okay, so even if you move that one, it would appropriately apply the red, green, and blue channels filter to their respective channels. Okay, if that makes sense. So instead of just having like a pure instead of just having a 3x3 filter, if you have 3 channels, then it becomes a 3x3x3 volume. Okay, so you have a 3x3 filter, but then you have three of those, right? So you stack 3 of those. This one is for red, this one is for green, this one is for blue. So you have the 3x3x3 volume. Okay, and besides that, in one convolutional layer, there isn't only one filter, because of course we're trying to detect a lot of features. So you usually have multiple multiple filters in one conv layer. So let's say, for example, in a simple example, we have 2 filters. So and each one has the RGB. The second one also has the RGB. So in our RGB image, we apply the 3x3x3 filter here. It will produce for the first filter, it will produce this feature map, and then for the second filter, it will produce this feature map in green, and then we will stack those feature maps to produce the final output. Okay, so if you have, let's say, 256 filters, then the depth of your feature map is also 256, because you are each filter will produce one feature map. Okay, so if you have 256 filters, you will stack together 256 feature maps as well. So here we only had 2 filters, right? So we had 2 filters means you have 2 feature maps, and that is what we stack together. That's what we have. That's why we have depth of 2. Okay, so yeah, just be aware that for one convolutional layer, there's usually multiple filters, because we're not only learning like one diagonal or one X, we're learning a lot of different features, right? So putting all of that together, the convolution would look something like this. Okay, so you have the filter W0, so this is the first filter, and then the second filter here, and then you have 3 channels, right? So this is the first channel, second channel, and third channel of the image, and then you have 2 outputs, 1 for each filter. And you'll notice that there are zeros around the image. We call that padding. Okay, so we'll learn more about that in a while, but basically we add zeros to pad the image, so that when it becomes the window, like for example, reaches this part here, so it's not a clean 3x3 window anymore, because it's only looking at a 2x2 window. So that's why we add padding, so that those that are on the edges can still have like a clean 3x3 window, even if it's already at the end. Okay, so yeah, that's convolution, and it's showing the sliding window, right? So what are the hyperparameters for the convolutional layer? So what do you need to set? So of course you need to set how many filters in the layer should you put in. Okay, the filter size, so it could be 3x3, 5x5, 7x7, 11x11, but usually we just use the 3x3 or 5x5. In one layer, however, they should use the same filter size. Okay, so notice that we have many filters in one layer, but they can't have different filter sizes. Okay, they should have the same filter size in that particular layer. Now if you add another conv layer, it could have a different filter size, but in one layer all the filters should have the same filter size. Okay, and the next is stride, and that is by how much we move our sliding window. So for example, if we have a 3x3 filter, so let's say this is 3x3, and our stride is 1, so we just move 1 pixel to the right, and then this is the next window. But if we have stride is equal to 3, then that means that we'll move 3 pixels to the right, so that means that we're looking at the next window, so there's no overlap. Okay, like that. Okay, but if it's less than the kernel size, then of course there will be overlaps. Okay, so yeah, so that's the stride, meaning how much do you move forward, and that also dictates how much you move downward. Okay, so if you have, like, let's say if you've already finished this row, and then you're going to go down, if you have stride of 3 also, then you need to go 3 pixels down, so your next window is down here. Okay, but if it's overlapping again, then you start with the 3x3 here, and then on the next window, if it's stride 1, then maybe somewhere around here. Okay, and then the next window be somewhere around here, something like that. And then if you finish this row, you'll go to the next row, which is somewhere around here. But there's a lot of overlaps this way if you have your stride is less than the filter size. Okay, so there will be overlaps that way. Okay, so and then as I mentioned, you have padding also. So the padding puts zeros around the image if you want to, so that windows at the edge of the image also gets considered with windows, even if they are like only a 2x2 window. So if you pad that, it can still fit the 3x3 filter size. Okay, so if you have stride 1, it would look something like this. So you only move 1 pixel to the left and 1 pixel down. Okay, but if you have stride 3, then it would look something like this. So you're moving 3 pixels to the right and 3 pixels down, so there is no overlap. So it's up to you, but generally the bigger the stride, the smaller your feature map becomes. So you also don't want to shrink it too much, right? Because imagine going from this image, and then if you have the stride to convolve, your feature map just becomes a 2x2. So it rapidly decreases the size. And then as I mentioned, if you have a padding of let's say 1, then it will pad the image with a border of zeros, so that your windows at the edges become cleaner as well. So that is the convolution layer. Okay, so what do the convolution filters learn during our after training? So the low level features, or the earlier layers, will learn some low level features like edges, textures, patterns, and then later on in later layers, okay, mid-level layers, you also learn mid-level features. So you kind of combine the low-level features that you had. So combination of edges, combination of patterns, combination of textures, until in the later layers, in the deeper layers, you learn more high-level features. Okay, so yeah, so you kind of learn incrementally from low-level to mid-level to high-level features, and then you combine them in the later layers. Okay, so we mentioned feature maps earlier. Those are also known as activation maps, and basically the feature map is the output when we convolve the input and the filter. Okay, so yeah, that's what we call it, the feature map. And the feature map of this layer, okay, so the output of this layer becomes the input to the next layer. Okay, so we're feeding the feature maps forward. Yeah, so it becomes the input of the next layer. Okay, so we're done with the convolutional layer. Next type of layer for the CNN is called the pooling layer. So the pooling layer downsamples the feature map, so meaning it shrinks down the feature map. So you reduce the dimension and you only keep the important values, and this is to control overfitting. Okay, so by reducing the dimensions, by pooling, you reduce the number of parameters and you also reduce the computation. Okay, so an example of the commonly used pooling layers are max pooling and average pooling. So we look at max pooling. So for a max pooling, we'll look at some window. In this one, it's a 2x2 window. And then in the 2x2 window, we'll look for the max value. So in this one, it's 6. So we put 6 here. In the next 2x2 window, the maximum is 8. So we put 8 here. The maximum in this window, the blue one, is 3. So we have the max 3 here. And finally, in the gray window, we have max of 4. So we put 4 here. So basically, from a 4x4 feature map, it became a 2x2 feature map, only keeping the maximum values in each window. Okay, so you're downsampling, you're downsizing, but you're still keeping the important features. Okay, Of course, for the average pool, instead of getting the maximum, you're getting the average value within the window. Okay, so you just adjust the operation, and it's more or less the same. You're just changing whether it's max or average, but the idea is still the same. Okay, so the pooling layer lessens the impact of slight position differences, because for example, if that 6 here appeared in this position here of 1, or in the position of 6, it would still be declared as the maximum, right? So whether we found the feature in the top left or in the next level below it, it doesn't really matter, because by max pooling, if it's the maximum feature or the most important feature, then it would be it would win out in the max pool, right? So it lessens the impact of slight position differences. Now, what do you need to set for the pooling layer? What are the hyperparameters? So of course, the kernel size. So is it a 2x2 window or a 3x3 window? And then the stride. Okay, so the same terminology from the conv layer. Stride is how much you move to the left and downwards. Okay, so the common setting is a kernel size of 2 and a stride of 2. So it's a 2x2 window, and then you move 2 pixels to the right and downward afterwards, so there's no overlap. But as I mentioned earlier, if your stride is less than your kernel size, then there will be overlap. Okay, so you might want this, you might not want this. It's something to experiment. So yeah, you can try it later if you want to. Okay, so here's an example of a feature map that was max pooled. So let me figure out. So this is a 7x7 feature map. 7 oh. So 7x7 feature map, and the output after pooling is a 4x4 feature map. So the settings of this pooling, I think, is kernel size of 2x2, and then a stride of 2 also, which is the common setting that we mentioned earlier. So let's check. First, it should look at a 2x2 window right here, and indeed the max is 1. If the stride is 2, then it would move to the next window, which is here, and the max here is 0.33, which is here. The next window, the max is 0.55 right here, and then in the next window, well, it can't fit a 2x2 anymore, but given what we have, the max is 0.33. Okay, and then since that's a stride of 2, it will go down 2 pixels down, so max of 0.33 right here, and then you continue that along this column, and then go down right here. So same thing, 0.55 right here, and then on the last row, this will only have a 1x2 because it can't fit the 2x2 window anymore, right? But basically you're picking 0.33, 0.55. This window it's 0.11, and then on this window right here, well, it's only 1, so it's 0.77, right? So you'll notice that even if we downsampled the feature map, we still have the most important part, right? Or the important parts of the feature map, which is this diagonal right here. Okay, and that diagonal is still present in our resulting feature map, which was already pooled. So we reduced our feature map from 7x7 to 4x4, which is already good enough, because from 49 numbers, you now only have 16 numbers. So that's like a factor of 3, right? Because 16 times 3 is 48, I think. Yeah, so we reduce it by a factor of 3, just good enough, right? So if we check the other feature maps, then so we did this for this one, right? It's the diagonal is still here after pooling. You have the center here. Center is still kind of here in the pooling, although it's not entirely centered, but this is a 4x4, so there's no real center, like it's not odd, so 2 can be considered as the center in this case. And then the right diagonal right here, still kind of present right here, although it did kind of curve a little bit. So yeah, the majority of the important features that we want are still part of the feature map even after we pooled it, okay, and we even reduced the number of dimensions. So after that, you can apply the activation layer still. So you can apply non-linearity function to the feature map. So you can choose ReLU, leaky ReLU, but usually you just use ReLU for this one. So remember, ReLU is the simple function wherein after 0, so if it's after 0, it will just output 0, but if it's greater than 0, it will output the same number. So if it's greater than 0, we won't touch it. If it's less than 0, we'll convert it to 0. So we blacked out those negative values here. Okay. So we still kept most of the important parts of the feature map anyway. So the negative values were truncated to 0, and the important parts, which are the ones, are still the same. Okay, so activation layer just adds non-linearity to our ConvNet. Okay, so this first 3 layer types actually focus on feature extraction. So the conv layer, the pooling layer, the activation layer, they focus on feature extraction, or getting features, right? So they transform the input image into feature maps, and the feature maps become smaller because we're applying pooling, but fatter, okay, as the network goes deeper. Because our feature map is smaller, we can afford to add more filters since we are processing only a smaller size, or smaller dimensions right now. Okay, so as we go deeper, we can observe that the feature map becomes smaller in size but fatter. So let's see some examples. So for this one, from like a big image, right, and it only has a depth of 64, and then if we max pool it, it becomes smaller in size. But then to compensate for the smaller size, we can have more filters. So the depth now is 128, and then if we max pool it again, it becomes smaller, but then again we can add more depth, like 256. So more filters. So now we can have 512 here, 512 here, and so on. Okay, and for a particular architecture, which is VGG, we'll see it in a while. This is the visualization of how the feature map is being transformed. So from 224 by 3, so this is the original image, right? So you have 3 channels, and then you convolve it with 64 filters. So it still has the same size, but now has 64 different filters, and then you max pool it, so it gets reduced, the size gets reduced, so to 112 by 112, so it gets halved. But then you can compensate by having more filters. So from 64 filters, it becomes 128, and then you half that again, that size becomes from 112, it becomes 56. But because we reduced the size, we can make it fatter or deeper. So from 128 filters, on the next level we have 256 filters, and then we half it again from 56 to 28, but then from 256 we get 512 filters, so there's more. Okay, so that's the pattern. Becomes smaller, but it becomes fatter. Okay, so that is for feature maps. So take note that we can also stack the conv layer, the pooling layer, and the activation layer, so they are stackable. Okay, and this is possible because the output of one layer can become the input of the next layer. So we can do something like this. So we can stack from the conv, we can apply relu, and then we can pool, or we can also do conv, pool, and then relu. Okay, so doesn't really matter how you order it. So that's already part of the design of your network, but just know that you can stack conv layers, pooling layers, applying the activation together. So if you do that, you can stack them even more. So you can have conv relu, pool, conv relu, pool, so something like that. So you can go crazy with the combinations of different types of layers. So that's up to you. Okay, but this is possible because the output of the input and the output of each layer is very similar. They're all just feature maps, right? They're all just matrices. So as long as they have the same dimensions, you feed them to the next layer, it will become downsized, and then you feed that to the next layer. Yeah, it just keeps being fed forward, basically. So the first three layers will try to learn features, and they will try to learn that incrementally. So in the lower layers, or the first layers, they will try to learn basic features. So for example, if you're learning faces, maybe you can learn about the eyes, or the nose, or the area between the eyes and the nose, and the lips, and so on. So different parts of the eyes. So those are different filters. Okay, and then on later levels, later layers, or later depths, then they will be combined to form like face-like features, really. Okay, and then the same thing with cars. You can have like some edges, some circles for the wheels, and then later on you combine them in later layers to form actual cars. Okay, so yeah, it's incremental, the way that they learn the features. And then finally, the last type of layer for ConvNets is called the fully connected layer. We already saw this earlier. When we have fully connected nodes, it means that all nodes in one layer are connected to all the nodes in the next layer. Okay, so the hyperparameters, or what you need to set, are the number of nodes, of course, and the number of fully connected layers. So for the input layer of the fully connected, you usually receive the feature map from the conv, pool, activation stacks previously. So you receive that as a feature map, and then the hidden layers will try to connect and combine the different features for the classifier, and then the output will be the classifier itself. So it usually has the softmax activation to output the probability of each class. Okay, so it kind of looks like this. So you have feature maps from the conv layers earlier, so you kind of straighten that out, or you flatten it. So from a 2x2 matrix, it becomes just one giant row, and this becomes the neurons for the fully connected layer. So this becomes the input, and then you try to figure out the weights and the connections, which features contribute to predicting that it's an X, which features contribute to predicting that it's an O. Okay, so you learn those weights connections, and of course you're not limited to just one fully connected layer. You can stack them too. Okay, so you can have multiple fully connected layers. Usually you have two. Okay, so yeah, So all in all, it would look something like this. So from the image, you can apply something like a convolution layer, and then follow that up with the relu for non-linearity, and then conv again, and then relu again, and then you pool for downsampling, and then you conv again, and then relu, and then pool, and then the feature map here would be passed to a fully connected layer, and then another fully connected layer before giving out the output. Okay, so yeah, that's it for convolutional neural networks. So finally, since we know the different layer types, what would be the content of the model for the CNN? So first, of course, you need to know the architecture. You need to know the different what type of layer is in the first layer. So is it a conv? Is it a pooling layer? Is it a relu activation, and so on? So define the architecture, and then of course you need to know the filter weights in the different conv layers, and in the fully connected layer you also need to know the connection weights. So that is the contents of the CNN model. Okay, and as we mentioned, you kind of feed the image to the low level parts that has low level features, and then as you go deeper, these low level features are kind of combined to look for mid-level parts until you kind of figure out that, hey, this is this looks like a car, or this looks like a truck. Okay, and then you finally predict the class after doing the fully connected layers. Okay, so that is the CNN model. Now for training of the CNN, it's basically the same process as the training for neural networks that we mentioned earlier, but I'll just add some things that are unique to convolutional neural networks. First is data pre-processing. So these are some pre-processing techniques that you can do to clean up your image data. So first is resizing. So of course, usually your images are of different sizes, right? So you usually don't have control over the size of the images, so you usually resize them to a uniform size so that your input layer has the same, it's uniform size, right? And then you can also do something called centering, wherein you try to compute the mean value, or the mean image, meaning you take all of the image and then you take their average, okay, just by adding all of the images and then dividing it by the number of images. So you get the mean image, which is like the average image of everything, and then you subtract that mean image from the image itself. So you kind of center it because you are subtracting the average. Yeah, so that's one thing that you can do to pre-process your images before feeding it to your CNN. And then there's also normalization. You can also do this so that you can put the numbers in similar scales, so you can have normalization. Okay, so those are the three pre-processing techniques that you can do for your images. And then there's also data augmentation. Okay, so why do we need data augmentation? So we said that we need more data for training, right? But if you have a very limited data set or a limited training set, then you can do this data augmentation techniques so that your training set becomes a little bit bigger. Okay, so if you have one image, you can do like random crops and shifts, and to produce other images, right? So let's say you have an image of like a person here. So you can do a crop like this maybe, or a crop like this, or a crop like this, or a crop like this, and those 4 crops already contribute. So from one image you produced 4 images from the different crops. So you kind of increase the number of training images that you have by 4 times. The problem though is that there's a lot of correlation with the 4 images because of course they were taken from the same image. So yeah, but usually it works out just fine. So you can do random crops and shifts. You can also do things like okay, wait. You can also do things like horizontal flipping. So if you flip it horizontally or you mirror it horizontally, then it's more or less the same object, but it's a different image. Because if you flip, let's say it's a guitar, and then you flip it horizontally, then the guitar is mirrored, right? But then it looks the same to you, only flip, but for the computer this is already a bunch of different numbers, right? If we flip it. So that's also a good augmentation technique, flipping. And then you can also do random brightness changes, like you can make it darker or brighter, and even if it looks the same, but it will have a different numbers in the image, right? Or random color changes. So you can also tweak the colors a little bit, because maybe if it's a red car, you tweak it a bit and becomes a little bit maroon, I guess, but it's still a car, right? So even if the color changed, it's still an object of the same type, right? So you can do random color changes and even random contrast changes. So maybe you make the image darker, and it makes the object pop out better. So you could increase the contrast, you could lower the contrast, and it's the same object, but then it looks different to the computer. So these are some data augmentation techniques that you can use to be able to add more training images to your training process. Okay, so yeah. Now we also don't need to start training from scratch all the time. We can do something called transfer learning instead. Okay, so for transfer learning, you're assuming that you already have a pre-trained model. Okay, so there's already a CNN model that exists. It was pre-trained already for another task, and then you repurpose that model for your own task. Okay, so you can do it in two ways. You can use the early layers of the ConvNet that was already trained as a featured extractor, and then you train a new classifier on top of that. So remember that we have conv layers and pooling layers. Those act as featured extractors, right? So you can just use the feature extractor of that model, and then you train a new classifier according to your task on top of that. So you can do that, so that you don't have to learn the new weights of the features, or of the filters again. So you only need to use or to learn the classifier's weights this time. Or another option is you can fine tune the CNN. So you could maybe freeze the early layers, like you don't learn already the early layers, but you continue training the deeper layers, but with a lower learning rate. So you only change them by a small amount, to be able to answer correctly what your new task is. Okay, because of course this existing model was trained for another task, and then you're just transferring its learning to your own task and then fine-tuning it, right? So you can also do that. So this makes the training progress faster, because you're not starting from scratch, you're not starting from random weights, you're starting from some weights that are already proven to be good in another task, and it turns out that you can also use them as a starting point for your own task. Okay, and it also allows training with smaller dataset, assuming of course that they are kind of similar to your own task. Okay, so if you were doing like cars versus airplanes, and then you and then you try to repurpose it to detect faces, then maybe it won't be as effective, because you were doing cars and bicycles and other vehicles, and then you're trying to jump to faces, so it might not work. So it will work as long as the data sets that were used are kind of similar, okay, or there's overlap in the types of features that they are using. So example of transfer learning would be something like this. So if you're training from scratch, you're really learning everything from random weights up to the final model, right? But if you're transfer learning, maybe you have a pre-trained ConvNet that was trained on cats versus dogs, and then you use those features, you can fine-tune them and train a new classifier on top of that to maybe classify car versus truck or something like that. Okay, so yeah, there's already a lot of pre-trained convnets that exist that were trained on ImageNet. We'll learn more about that in a while. And then if you have a new task, then you can fine-tune those pre-trained models, so you update the weights by a little bit so that you can repurpose them for your own task. Okay, so that is transfer learning. Okay, so now that we know about convolutional neural networks, let's take a look at its history and look at some of the architectures that had some major contributions to the development of CNNs. Okay, so first off, we have the Neocognitron in 1979. This was created by Kunihiko Fukushima, and this is widely recognized as the first convolutional neural network, and it was used to recognize visual patterns and used for Japanese handwritten character recognition. So even in the 1979, it was already present, right? So the Neocognitron kind of looks like this. Okay, so convolutions. And the next one is the LeNet architecture in 1990. This was created by Jan LeCun, okay, one of the famous researchers in neural networks. And he used the MNIST dataset, which is a dataset for handwritten digits, for the LeNet. Okay, and the LeNet is used for reading zip codes and digits. Okay, automatic reading of zip codes and digits, and it was the one that used backpropagation for CNN. So it was the first one who used backpropagation for CNN. So the LeNet architecture looks like this. So the input is a 32 by 32 image of only one channel, so it's a black and white. Okay, and then there's a convolution, 5 by 5 convolution, so it produces a 28 by 28 feature map. There's only 6 filters. Okay, so 6. So you have the 6 feature maps here, and then you pool. They use average pooling instead of max pool. Okay, and then another convolution, so it's a 5 by 5 convolution, so it produces a feature map of size 10 by 10, and then subsampling 5 by 5, and so on. Okay, so these are the layers of LeNet. It only has 5 layers, so convolution, average pooling, convolution, average pooling, convolution. So 3 convolutional layers, and then 2 fully connected layers. And you'll notice that the activation function were hyperbolic tangent, so it's not yet ReLU. Okay, so that was because hyperbolic tangent was the famous activation function at this time. Okay, so yeah, that's LeNet. And then to see it in action, we have the following illustration. So kind of looks at digits, handwritten digits, and then it will give you the answer. Okay, so that is the LeNet. Then next, in 2000s, the neural network hype died because of the vanishing gradient problem. And in a nutshell, this problem is that the information from the input to output layer gets lost because the gradient is too small sometimes. So that's why it's called vanishing gradient. So sometimes when we try to find the gradient in gradient descent, the gradient is too small and the update is too small, and it kind of stops learning at that point. Okay, so because of this vanishing gradient problem, a lot of neural network research stopped, and the focus shifted to handmade and designed features. So this was when the rise of the SIFT features, the HOG features came to play in the 2000s. But then in 2006, there was a comeback for the deep learning research because of the study of Geoffrey Hinton and others. He created a learning algorithm for deep belief networks, and it brought back interest in deep learning. Okay, so this was in 2006. And then in 2008, Andrew Ng of Stanford advocated for the use of GPU for training deep neural networks. And this allows you to speed up the training by many folds. Okay, so, and it also allows you to train on huge volumes of data efficiently. So in 2008, this was the start of the usage of GPU for training deep neural networks. Now, it allows you to train on huge volumes of data efficiently, and so that's why we need big data. Okay, and in 2009, ImageNet was launched, headed by Dr. Fei Li, also from Stanford. The ImageNet contains 14 million labeled images. So this is really big data because there's 14 million images that are labeled. Okay, and they also launched the ILSVRC, or the ImageNet Large Scale Visual Recognition Challenge. So this was done yearly, competition that uses the ImageNet dataset for visual recognition or classification. So you use 1.2 million images for training, and there's 1,000 different classes. Okay, so imagine that, having to classify an image into one of 1,000 classes. So it's kind of a difficult task. That's why the ImageNet is used as a benchmark for CNNs. Okay, so how does it do on the ImageNet? And if it's doing well, then you probably have a good network architecture. Okay, so the first in the previous year, it was the GPU, so that was needed for deep learning. The second one in 2009 was the lots of data, and that is ImageNet. The only thing remaining is that we still have the vanishing gradient problem, right, which was the reason why the neural network research kind of died down. And this was solved in 2011. So there was a solution that was proposed for the vanishing gradient problem by Joshua Bengio, Antoine Bordes, and Xavier Glorot, the same Xavier Glorot who created the Xavier initialization, the weight initialization. Okay, so the three of them published a solution for the vanishing gradient problem, and the solution is part of the solution is to use ReLU activation function instead of the famous at that time hyperbolic tangent. So instead of using hyperbolic tangent, you just replace it with the simpler ReLU, which allows you to train for deeper neural networks, and it's also kind of solves the vanishing gradient problem. So with this, you now have the GPU, the lots of data, and you have a solution for the vanishing gradient. So it was at this point, but by the next year, in 2012, one of the landmark architectures for CNN was AlexNet, and AlexNet won ILSVRC, the competition that I mentioned earlier, for 2012. So AlexNet was created by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton, and they were the winner of the 2012 competition with a 15.4% error rate. So that means that they were around 85% accurate for 1,000 classes. Okay, imagine that, 85% accurate. And The reason why it was so popular is because there was a huge gap between AlexNet and the second placer, which uh, had 26% error. So there was around 10% gap between the first place and the second place. So it really was a huge success at that time. So because of this success, resurgence of the CNN research was brought back. Okay, there was resurgence in CNN research, and then um, deep learning was brought back to the mainstream because of this success. Okay, and they used the research from the previous year to use ReLU instead of hyperbolic tangent, and they were also the ones who introduced dropout and data augmentation to avoid overfitting. Okay, so the dropout layer is actually due to them. So this is the illustration of the architecture of AlexNet. Now if we dive deeper into it, this is the architecture in detail. So you have the conv layer with 96 filters, and the filter size is 11 by 11. Okay, all of the activation functions are ReLU, by the way. Okay, and then after the conv you have a max pool, and then a conv again with this time with 256 filters, and then this one is a 5 by 5 with a stride of 1, and then max pool again, and then 3 successive conv filters. You have 384 filters here, 384 filters here, and then 256. And then they were similar filters with a 3 by 3 filter size with a stride of 1. So their filters are actually overlapping because you have a filter size of 3 but only a stride of 1, so they have overlapping conv and even the max pool. Okay, and then you have the dropout here, fully connected layer, dropout again, and then 2 more fully connected layers. And then for this one, the size was 4096 neurons, 4096 as well, and then 1000 neurons at the end because there were 1000 different classes. And then you apply the softmax activation to have the final probabilities of each class. Okay, so that is AlexNet. Now the next one was VGGNet in 2014, created by Karen Simonian and Andrew Zisserman. They were only the runner-up for the 2014 competition, but they had a very good error rate, which is 7.3% error. So from 15% error rate of AlexNet, it went down to 7.3% error rate for VGGNet. And its important contribution was that they discovered, or they showed, that the depth of the network is critical for good performance, because they had the version of VGGNet with 11 layers. It was good. So they tried 13 layers, it was even better, and then they tried 16 layers, it was also even better than 13, and then they tried 19 layers, so it stopped improving, so they stopped at 19 layers. So when we talk about VGGNet, it's usually either the VGG16 or VGG19 that we're talking about. Okay, so yeah, that was their major contribution, that depth matters. Okay, and for VGGNet, they also used homogeneous architecture, meaning the filters in the convolution, the conv filters and the pooling kernels were the same all throughout. Okay, so 3 by 3 filters and 2 by 2 pooling. So I already showed you a similar example earlier, showing the feature map of VGG, how it transforms the image into a smaller feature map but then fatter. Okay, so let's take a look at the architecture and compare it with AlexNet. So for AlexNet, it had different filter sizes, right? So you have the 11 by 11, 5 by 5, 3 by 3, and then the max pool all has 3 by 3. But in VGGNet, they were all homogeneous or uniform. So all of the conv filters are 3 by 3. All of the max pool are 2 by 2. Okay, so unlike AlexNet, so you have a conv pool, conv pool, conv pool, and then 3 convs in a pool, 3 convs in a pool, and then 3 fully connected layers, with the final one having 1000 neurons for the 1000 different classes. Okay, so yeah, that's the architecture of VGGNet. Now, VGGNet was not the winner of 2014 because the winner was GoogLeNet, created by Google researchers led by Christian Szegedy. Okay, so they were the winner of the ILS VRC 2014 with a 6.7% error rate. So remember, VGGNet was like 7 point something. This one is only 6.7% error rate. So they kind of created a different architecture. They introduced something called the inception module, which we'll see in a while. But yeah, they kind of strayed away from the AlexNet type architectures, which is just stacking layers one after the other. So the inception module kind of yeah, is the center of their architecture. So it has 22 blocks of layers, but if you unravel it, it spans over 100 layers in total. And the curious thing about this is it doesn't have fully connected layers at all. Okay, so just a bunch of inception modules, and it actually reduced the number of parameters in the network. So GoogLeNet only has around 7 million parameters compared to AlexNet's 60 million parameters. Okay, so even without fully connected layers, it had a very good error rate, and it even reduced the number of parameters that you need to train. Okay, so at this point, there were several problems in deep learning that they wanted to address, the GoogLeNet team. So if you have a bigger model, then you're more prone to overfitting because you have more parameters, right? Especially if your training set is small. Then if you have a small training set and if you have a big model, then you're basically looking at the same thing over and over again. So you're kind of memorizing it instead of learning something more general, right? And so you have a bigger model, you have more parameters, and if you have more parameters, then you have to do more computation because you have to learn a lot more weights. Okay, so and if you have more computation, of course you have limited amount of computing power, so you need to take that into account. So their solution to this was, instead of doing like fully connected layers, they wanted to create something called a sparsely connected network. Okay, so for a densely connected network, you have one layer connected to the next layers connected to the next, and so on. So this was the prevailing architecture at the time, like AlexNet, VGGNet. They just stack conv layers, pool, conv pool, and so on, and then fully connected layer on top of that. But for GoogLeNet, they wanted to try something called a sparsely connected, which kind of looks like this. So from one layer, you have a choice to go to 3 different layers, and then you combine the answers for the 3 layers. Okay, so in sequential stacking, which is for the normal CNN, you can stack a 3 by 3 conv, 5 by 5 conv, and then max pool, and so on. And one layer can only have one filter size, right? But it turns out that you don't always have to stack them sequentially, because non-sequential architectures could even be better. Okay, so they did this by creating the inception layer, or the inception module. And what it does is it processes visual information at various scales, and then you aggregate. Okay, so it performs a kind of a dimension reduction technique by doing stacked 1 by 1 convolutions. So it has a 1 by 1 convolution. So 1 by 1 window means that you're looking at individual pixels actually. So they found out that you can reduce the computational expense by doing the inception layer. So the inception layer kind of looks like this. So from the previous layer, you have a path to just using 1x1 convolutions, right? Or you can have 1x1 followed by a 3x3, or a 1x1 followed by a 5x5, or a max pool, a 3x3 max pool followed by a 1x1. So you have these 4 paths, 4 different choices, and then you concatenate the results of each one after that. Okay? So you're kind of looking at them at different scales. So you have only 1x1, 1x1 3x3, 1x1 5x5, and then max pooled, and then 1x1. Okay, so you're looking at different scales and then combining their answers. Okay, so concatenate the 4 filters after that. So the GoogLeNet architecture actually looks like this, and the ones that I wrapped in the rectangle are the inception modules. Okay, so yeah, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 inception modules in total. And for the breakdown, you have the following. So you have a conv layer, a max pool layer, conv, max pool, and then the rest are inception. So inception 1, 2, max pool, inception, 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 max pool, and so on. Okay, they even use an average pool here somewhere, and then they also use a dropout and then a softmax. So there is no fully connected layer at all in here, and you'll notice that the number of parameters are only in the thousands, not in the millions, but the number of operations are in the millions. But this is okay because as long as the number of parameters that you're training is low, then you are not really you're lessening the chance of overfitting. Okay, so yeah, that's GoogLeNet. Okay, next architecture that also had some impact was ResNet, or the residual networks. Remember, GoogLeNet was created by Google researchers. ResNet was created by Microsoft researchers this time, and it was led by Kai-Ming He. Okay, the same Kai-Ming He that created the He initialization, the weight initialization that we mentioned earlier. Okay, they were the winners of the 2015 competition with a 3.6% error rate. So imagine that, 96% accurate on 1,000 classes. So that's bonkers. That's really good. And this one even achieved higher accuracy than humans, because humans are estimated to have error rate of 5 to 10%. So it even has better performance than humans. Okay, and it has 152 layers, so it's really deep. But the way that it counters overfitting is by using residual blocks. Okay, so remember, we have 152 layers, so it's really deep. So how does it prevent overfitting? So it does residual blocks by doing skip connections or shortcuts to jump over some layers. Okay, and it also heavily used batch normalization. So the skip block or the residual block looks like this. So for a regular block, you kind of feed it forward, right? You have the wait, activation, wait, and then feed it forward. But for a residual block, you have a path here that you can take. So instead of going through this layer, you can skip all the way up to the end. Okay, you have a choice of skipping all the way to the end. Okay, so that is the main contribution of ResNet, the residual block. Okay, so if you compare the 34 layer version of the ResNet, compare that to VGG19. So VGG19 obviously only has 19 layers, and then this one has 34. But even if it has very deep architecture, it counters overfitting by adding this skip connections or the residual blocks. Okay, so that is ResNet. And then finally, there's also DenseNet in 2016, which was created by Facebook AI researchers, and they tried to combat the vanishing gradient problem by doing dense connections. So what they do is they connect every layer directly with each other. So it encourages feature reuse because what the other layer learns can also be passed on to later layers. Okay, so it kind of looks like this, right? So for DenseNet, this layer is connected to all the other layers. This green layer is connected to all the other layers, and so on. So that is the dense connection. It's that it's all connected to all the other layers. So if we compare the standard CNN, it kind of looks like this, just standard feed forward. For ResNet, you have the skip connections, and then for DenseNet, you have everything. So everything is connected. Okay, so it's even more complex than ResNet. Okay, so that is DenseNet. Now, of course, CNNs are not just limited to classification. So there are other computer vision neural networks like the RCNN for object detection. So RCNN stands for regions with CNN features. Okay, so it kind of looks at an object and focus on some regions to detect the object of interest. And there's also YOLO, or you only look once, for object detection. Okay, so it kind of does one-shot learning. Look at it once and then try to figure out whether the objects of interest are there. You have the UNet network, the UNet architecture for segmentation. Okay, so it's named as so because of it looks like a U. There's also the neural style transfer networks. So for neural style transfer, you're given an image and another an artwork basically, or the style of artwork, and then you try to combine the two. So you have this Ferrari in the style of the Starry Night, and then maybe this forest in the style of like this art here. So they kind of combine the style of this artwork to the another image. So that is neural style transfer. Okay, and then another one is something called the deep dream. So I'm not sure if you've seen this already or if you're familiar with it, but basically it enhances features in the image, and the result is kind of disturbing, to be honest. So try to look up deep dream and you'll see some nightmarish images, like for example this one, the picture of Starry Night with like bunch of weird like circles and eyes, and then Mona Lisa with like pigeon heads and animals around it. So yeah, just look up deep dream, and if you don't want to sleep tonight or whatever yeah, but yeah, that's it. So that's it for convolutional neural networks. And to summarize, so in this very long video, we learned first about perceptrons, which is the basic building block of a neural network. It takes in a bunch of inputs. It has a set of weights and a bias. It takes the weighted sum of the inputs, and then it passes the sum to an activation function to determine if it would output 0 or 1. Okay, and then if you use a bunch of perceptrons together and arrange them in multiple layers, then you have a neural network. Okay, so we talked about what you need for your neural network training, which is your like learning rate, weight initialization, your loss function, and so on. Okay, we also talked about how to train the neural network by doing gradient descent and backpropagation. We talked about the different types of neural networks, like multi-layer perceptron. You have the convnets. You have the generative adversarial network, or the GANs, the autoencoders, LSTMs, and so on. What else did we learn? We also talked about deep learning, which is deep neural networks, and that we need lots of data, lots of training data, and GPU for training. Okay. Okay, and then of course we talked about convolutional neural networks. They use filters. Filters just learn your features basically. So if you have a diagonal feature, edges, patterns, textures, and so on, so the filter will learn that for you. Okay, and then for other conv layers, for CNN layers, you have the conv layer, the pooling layer, activation layer, and then fully connected layers. And then we also looked at the important architectures for CNN like AlexNet, VGGNet, GoogLeNet, what else? ResNet, and the DenseNet. Okay, we also looked at the history of CNN and how it progressed and developed. Okay, so hopefully you learned something from this very long lecture video. If you have any questions, please don't hesitate to ask me, and I will see you in the next video.